Hello there and welcome to the Sleepyometry channel. Tonight you begin with the illusion of stillness. The room is quiet. The air barely stirs. Yet beneath you, beneath every bed, every street, every ocean and continent, the planet moves. Not with noise or tremor, but with the long invisible rhythm of its own breathing. The ground that feels eternal is in truth alive. It expands, contracts, cools and rises. Beneath the surface, stone flows like slow honey. Heat seeps upward through cracks older than time. So before we continue, hit like and subscribe so you don't miss a single revelation as this story unfolds moment by moment in real time. Tell me in the comments where you're watching, from what time it is there, and whether you believe we're hearing the whole truth about what's unfolding above our heads. And if you want to keep the signal alive, share this video on X, Facebook, Reddit, or even just with the people who still look up at night. You are the reason we can keep following the impossible, and for that, thank you. If you could see the Earth in motion sped up 1,000,000 times, the continents would drift like clouds on a molten sea. Mountains would ripple upward, crumble and rise again. Oceans would open and close as if the planet itself were inhaling and exhaling. You would see ice creeping down from poles and retreating again like the slow beat of a planetary pulse. From this distance, the world would not appear solid at all, but fluid, its skin folding and unfolding, its heart glowing red. For billions of years, that pulse has never stopped. Long before the first cell divided, long before the first light of a sunrise touched a human eye, the Earth was already alive, reshaping itself in silence. Mountains that once towered where you sit now have vanished to dust. Oceans that once drowned continents are gone, replaced by others still young enough to remember fire. Every cliff, every grain of sand, every fossilized shell tells the same quiet truth: nothing here is fixed. To imagine the Earth's story, you must stretch the boundaries of time until 1,000,000 years becomes a breath. Imagine rivers carving canyons not by violence but by patience. Imagine continents wandering apart, taking forests and creatures with them like passengers on slow ships. The surface shifts, the sky evolves, and all the while the deep Earth below remains restless. In laboratories, scientists call this geodynamics, the constant churning of the mantle, the convection of molten rock beneath the crust. But those are merely words for something much older and grander: the planet's heartbeat. The heat that drives this heartbeat was born with the Earth itself. 4.5 billion years ago, as dust and stone collided in the young solar system, gravity gathered them into a growing sphere. Each collision released energy heat so intense it melted the forming planet from the inside out. That primal fire never died. It still burns in the core, fanned by the slow decay of radioactive elements, keeping the deep Earth molten and alive. Without it, the planet would be cold and silent, a frozen rock adrift in space. Instead, it breathes. Sometimes that breath reaches us. It rises through volcanoes, whispering from vents in the sea. It hums through fault lines, shifting mountains by inches. Even when the world seems calm, the crust beneath our feet trembles with tiny earthquakes too faint to feel. Sensitive instruments record thousands of these murmurs every day, a planet, adjusting, stretching, sighing. We live atop an enormous lung of stone, always expanding and contracting. If the Earth was scaled down to the size of a single human body, its crust, the layer we call home, would be thinner than the skin of your eyelid. Beneath it, molten rock circulates like blood, transferring heat. Outward, cycling minerals inward, feeding volcanoes, birthing new land at mid-ocean ridges while swallowing old crust at deep trenches. Each process depends on the others in perfect, endless balance. Creation, destruction, renewal. The ancients sensed this motion long before science could measure it. To them, the planet was a living being. The Greeks named her Gaia. In Andean myths, she was Pachamama. To the Navajo Nihuka Diin, Earth Mother whose breath gave life to wind and stone alike. Modern geology in its own way agrees. We have discovered the physics beneath the poetry, yet the truth remains the same. The Earth is not an inert sphere of rock. It is a dynamic organism powered by heat, sculpted by time and breathing, in cycles that make human centuries vanish into insignificance. Consider the crust itself, a mosaic of immense plates drifting over molten currents. At their boundaries they grind and collide, forming mountains and trenches, continents and oceans. Beneath the Pacific, a plate slides under another, creating the volcanic ring that circles it in fire. Under the Himalayas, India still presses northward into Asia, forcing peaks toward the sky. In the Atlantic, new crust rises from a deep scar that runs down the ocean's heart, widening the sea every year by the width of a fingernail. These motions are slow yet unstoppable. The shape of the world you know is only a temporary version of Earth's ever-changing face. Every breath of the planet leaves its mark. When it inhales, continents converge, mountains rise, and landmasses fuse into supercontinents. When it exhales, those same masses crack and drift apart, birthing oceans and archipelagos. It has happened not once, but many times, cycles of assembly and breakup stretching back billions of years. Each rearrangement rewrote the climate, the chemistry of the air, and the direction of evolution itself. Life has always danced to the rhythm of geological breath. Yet for all this movement, the planet is gentle with us. Its changes unfold so slowly that to human eyes they seem non-existent. We walk across ancient rock and call it permanent, though it is only resting between transformations. Even the ground beneath your feet, stone, soil, city foundation, floats lightly atop the mantle's invisible tides. You are standing on motion itself, carried forward by a process that began before life and will continue long after. Close your eyes for a moment and imagine it. Far below the silence of your room, heat ripples through the mantle like the glow of a sleeping heart. Entire mountain ranges shift by fractions of an inch. Microscopic crystals realign under pressure. Iron deep within the core stirs, creating invisible magnetic fields that sweep out into space, shielding the planet from solar winds. Oceans swell and fall with the moon's pull, carving coasts that look unchanged but never are. The Earth moves beneath your pulse, and your pulse answers it. This, then, is geology, not a record of the dead past, but the study of a living planet. To understand it is to see time differently, not as a line, but as a tide. Everything changes, yet everything remains part of one breathing system, from molten core to drifting cloud. Tonight, as you listen to the quiet, remember the stillness beneath you is an illusion. The Earth turns even now, revolving around the Sun at 90 miles per second. The crust creeps, the mantle flows, the core spins faster than the rest. You are lying on the surface of a world that never stops moving, though it moves too slowly for the human heart to notice. The planet does not sleep. It only rests between beats. And if you listen long enough, beyond the hum of cities, beyond the rustle of wind, you can almost hear it, the slow, steady breathing of the Earth itself. If you could shrink the Earth to the size of an apple, the layer that holds every ocean, forest and city would be no thicker than that fruit's skin. It's a startling thought. The solid ground we trust with our weight, the mountains that scrape the sky, the trenches that dive miles deep are all part of a shell so delicate it could peel away in a single motion. Beneath it lies the mantle, a vast ocean of slow-moving rock that circulates heat and minerals like a living bloodstream. The crust floats upon it, light and brittle, drifting as fragile rafts on molten seas. Imagine slicing that cosmic apple. Beneath the paper-thin crust, the color changes, darkening through layers of compressed minerals, until the slice glows red within a fire. That fiery realm is the mantle solid in one sense, yet flowing over eons like honey under heat. The continents and seabeds above it are passengers on this slow current, their journeys invisible in a lifetime but monumental across ages. To grasp this scale is to understand how delicate the surface world really is. Everything we build, everything we are, rests on a layer so thin it would vanish if the planet were scaled down to your hand. This awareness changes perspective. The tallest mountain, Everest, rises just 9 kilometers above sea level, a fleck of dust compared to Earth's diameter of more than 12,000 kilometers. The deepest ocean trench descends about 11. Together, they barely dent the sphere. If the planet were smooth covered by the oceans it already holds, the water would swallow it completely, and the crust would disappear beneath a perfect curve of blue. Our landscapes, dramatic as they seem, are wrinkles on a cooling fruit. And yet this thin shell holds all known life. Within its first few kilometers, roots stretch, animals burrow, humans dig. We've never touched the mantle directly. Our deepest mines and boreholes reach less than a third of the way through the crust. What lies below is known through echoes, the way a doctor listens to a heartbeat. Seismic waves from earthquakes travel through the planet and return altered, revealing layers of density and heat. By listening to those tremors, scientists have drawn a portrait of the unseen world beneath our feet, a world still molten, restless and alive. The crust itself is patchwork, continental and oceanic, two types of skin with very different stories. Continental crust is thick, buoyant and ancient, some parts more than 4 billion years old, survivors of Earth's earliest days. Oceanic crust, dark and heavy with iron, is forever young, born anew at mid-ocean ridges and recycled back into the mantle after a mere 200 million years. Together they form a moving mosaic that never stops shifting. Land and sea trade places through time. What is mountain today may sink tomorrow beneath waves. Look more closely at that boundary where crust meets mantle, the Mohorovicic discontinuity, named for the scientist who first detected it in the vibrations of an earthquake. To him, it was a sudden change in sound, a subtle echo deep underground. To us, it is the base of the world. We know the line between the stable and the molten, between the temporary and the eternal. Above it lie sediments, fossils, cities and dreams. Below it, a world without air or light, where pressure turns minerals into crystals harder than steel. The thinness of the crust is also the secret of Earth's vitality. Because it is fragile, it cracks. And through those cracks, heat escapes water cycles, and life finds chemistry. Volcanoes vent gases that become air. Hydrothermal vents build minerals that host living cells. The crust's weakness is what keeps the planet alive. A thicker shell would trap its interior heat until it suffocated in its own stillness. A thinner one might have burst long ago, but here on this narrow line between fire and sky balance was found. From space, astronauts often describe the planet's edge, the thin blue veil of atmosphere, and the faint curvature of land below. They say the Earth looks delicate like glass suspended in darkness. Few realize that what they see is not just fragile air, but also the unseen fragility of rock. The continents beneath that glowing edge are thin as breath, yet strong enough to cradle oceans and weather continents of ice. That tension between delicacy and endurance is the essence of geology power concealed beneath stillness. Sometimes when you press your palm to the ground, you can feel a faint hum, the vibration of distant machinery, the rhythm of footsteps, the whisper of the planet's own tremor. Beneath that hum, deeper still lies the motion of continents sliding on currents of molten stone. You can't feel it, but it's there, the planet's slow exhalation, steady and unstoppable. The crust flexes and bends with tides of rock the way an apple's skin shifts over its swelling flesh. Think of that when you see a mountain or a canyon. Think of it when you watch waves crash on the shore. Those forms are not permanent fixtures, but temporary sculptures carved on a fragile rind. Every stone, every cliff, every plane is part of that skin, infinitesimal on a cosmic scale, yet immense to us, because it holds everything we know. The Earth's thin crust is both boundary and bridge, separating us from the deep fire below, connecting us to it through heat and minerals that rise from the mantle's heart. We are surface creatures, children of this narrow zone between flame and frost. And as we rest upon it, on a skin thinner than an apple's peel, the planet turns beneath, breathing quietly, holding us in its patient, endless motion. Long before there were forests or oceans shaped as we know them, the Earth's surface was a restless sea of fire. Beneath its thin crust, molten rock surged upward in slow, glowing rivers, currents of heat and light seeking a way toward the cooler air above. Each pulse of magma was a breath of the planet's deep interior, a silent uprising of energy stored since the dawn of its formation. Over eons, these glowing rivers cooled, solidified, and turned to stone. What once flowed like liquid flame became granite, the quiet heart of mountains. Granite is not just rock, it is crystallized time. Deep underground, when magma stalls on its way upward, it begins to cool, slowly allowing minerals to grow and interlock. Feldspar, quartz, mica. Each mineral takes shape in perfect order, like notes in a symphony conducted by pressure and patience. As the magma cools, gases bubble and escape through cracks, forming veins of quartz that glint like frozen lightning. Every crystal is a memory of temperature and chemistry, a fingerprint of the planet's internal rhythm. Imagine standing in Yosemite Valley and running your hand across the face of El Capitan, a wall of solid granite that rises more than a kilometer above the valley floor. What you touch was once molten light, glowing and moving miles beneath the surface. It hardened there, entombed in darkness, and only after millions of years of uplift and erosion did it emerge into the sunlight again. The same story echoes across the Scottish Highlands, the Canadian Shield, and the Sierra Nevada landscapes sculpted from fire cooled into endurance. When magma rises but never erupts, it leaves behind vast underground bodies called plutons, slowly cooling chambers of liquid rock that solidify into granite. Some plutons span hundreds of kilometers, forming the roots of entire mountain ranges. As surrounding rocks erode away, these buried hearts are revealed like the bones of the earth laid bare. What we now climb, build with, and carve into monuments are the remnants of those hidden magmatic seas. Each granite outcrop is a page from a story written in heat. The speckled texture you see, the balance of pale feldspar, smoky quartz, and shining mica, is the record of its slow birth. If the cooling had been faster, no crystals would have formed, and we would have obsidian, instead volcanic glass born in haste. But granite was never in a hurry. It is the patience of geology made visible, the art of transformation practiced over millions of years in complete darkness. At the microscopic level, granite tells of movement and tension. Some crystals grew undisturbed, others were twisted and fractured as the magma chamber shifted. Tiny lines called flow bands mark the currents of molten rock frozen mid-motion. Geologists read these patterns as you might read the grain of old wood following the direction of a vanished flow. In this way, granite is both sculpture and script. It shows how the earth once moved, then holds still forever. Its strength has shaped civilizations. The pyramids of Egypt, the temples of India, and the monuments of Rome all draw endurance from granite's unyielding nature. To quarry it is to challenge the patience of stone. To carve it is to converse with time, and yet even this seemingly immortal rock will one day return to dust. Rain, frost, and the roots of trees pry open its fractures. Grain by grain, the mountain melts back into the rivers that once flowed as fire. The chemistry of granite also hides a secret. It is lighter than the basaltic rock of the ocean floor. That difference is why continents float higher on the mantle than seas do. The same magma that forged granite also gave Earth its balance between land and water. Without it, there would be no dry ground, no valleys for rivers, no cradle for life. Granite is the foundation of habitability, a quiet gift from the planet's fiery youth. And there is beauty in its transformation. When sunlight catches the surface of a weathered granite boulder, the mica within it flashes like trapped starlight. Those glimmers are not reflections from outside, but memories from within minerals that once shimmered in molten heat, now shining through the cool crust. To touch granite is to touch a pulse that has slowed almost to stillness, but never quite died. Across the world, from Yosemite's silver domes to the ancient cliffs of Aberdeen granite, carries the same truth. What appears solid and eternal was once fluid, luminous, and alive. Each mountain is a monument to change. The fire turned to stone, the motion turned to memory. The earth may seem quiet now, but beneath every granite ridge its heart still burns, preparing the next chapter of transformation. The rivers of fire have become rivers of time, and in that slow metamorphosis the planet reminds us of its nature. Nothing fixed, nothing wasted, everything in motion, even stone. Far below the surface, where heat glows like the breath of a buried star, carbon learns how to endure. It begins as the simplest of elements, one shared by every living thing, from leaves to bones, from soot to the graphite that writes our stories. But in the hidden vaults of the mantle, that same element faces pressures millions of times greater than the weight of the atmosphere. The atoms, forced closer than they ever wished to be, rearrange themselves into the tightest possible lattice, a perfect symmetry of strength and light. In that silence, carbon becomes diamond. No sunlight ever reaches these depths. The air is crushing the temperature fierce enough to melt iron. Yet in that place of extremes, perfection takes shape. Each diamond begins smaller than a grain of sand, growing over millions, sometimes billions of years, as carbon atoms lock into the precise geometry of tetrahedral bonds. It is nature's most disciplined architecture, a crystal born from chaos built entirely by pressure and patience. The journey of a diamond does not end in the dark. To reach the world above it must hitch a ride on one of the planet's rarest and most violent events, a volcanic eruption from deep within the mantle. These eruptions do not flow like lava from ordinary volcanoes. They explode upward in narrow funnels called kimberlite pipes, racing through the crust at incredible speed. In a matter of hours, material from depths of nearly 200 kilometers is hurled toward the surface. The diamonds survive only because the ascent is so rapid that they never have time to melt back into graphite. Geologists call them messengers from the deep. Each diamond-bearing kimberlite carries information from the planet's hidden interior, tiny time capsules of pressure, temperature, and chemistry sealed within the stone. Trapped inside some are microscopic minerals unlike anything found at the surface, relics from layers of the earth we have never seen. Studying them is like holding a postcard from the mantle written in the language of atoms. When these fiery messengers finally cool, they leave behind vertical scars in the crust pipes that miners later chase through ancient rock. Within them lie crystals that gleam with the light of all they have survived: the crushing of continents, the folding of mountains, the rise and fall of oceans. Some are flawless, clear as frozen air. Others are clouded, bearing inclusions that tell their history like birthmarks. Under the microscope, scientists can trace the rhythm of their growth rings, each one marking a stage in their impossible ascent toward the light. What makes diamonds so enduring is not magic, but physics. Their atomic structure is the densest arrangement carbon can achieve. Every atom shares its electrons evenly with 4 neighbors, creating a network that leaves no room for weakness. This symmetry allows light to bounce and scatter through the crystal, splitting into the colors of fire. In that brilliance, the universe shows us one of its simplest truths: beauty is often a byproduct of endurance. For billions of years, diamonds waited in darkness long before any human hand could find them. Some formed when the first continents began to cool, when the sky was still thick with volcanic ash. They are older than coral reefs, older than trees, older even than the moon's familiar face. To hold one is to touch the Earth's memory, the same carbon that once drifted through the atmosphere as invisible gas, now locked into eternity by the patience of pressure. And yet, for all their perfection, diamonds are not rare in the way we imagine. The mantle may hold countless trillions of them scattered like stars across the deep. What is rare is the chance for them to rise to travel through a kimberlite eruption that preserves their structure and sets them within reach of sunlight. Those that survive this violent birth are miracles of timing. Each crystal is both fragile and immortal, a survivor of fire and crushing gravity that somehow arrives intact, waiting for someone to notice its quiet gleam. In a poetic sense, a diamond is the planet's autobiography written in carbon, each facet a reflection of pressure, each sparkle a memory of heat. It is a paradox made tangible, something formed in darkness that exists only to shine. When light passes through its lattice, it bends, refracts, and scatters into a storm of colour. That dance of light is not decoration. It is the echo of the forces that created it, the whisper of the deep earth turned visible. If you look closely into a diamond, not the polished gem but the raw crystal, you might see tiny fractures, trails of inclusion, or faint halos of strain. They are imperfections, yes, but also proof of survival. Even perfection needs a history. Even light requires shadow. Every diamond, no matter how small, is a reminder that beauty can come from unbearable conditions, that pressure does not always destroy, sometimes it refines. From carbon dust to crystalline fire, from buried darkness to the open sky, these stones carry the lesson written into the bones of the earth itself. What endures is what transforms. You stand before a mountain and feel the stillness. It seems eternal, unchanging, as if it has always been there and always will be. But the truth is that even mountains breathe. Not in the way lungs do with air and rhythm, but through the push and pull of stone. Every peak is a frozen moment in motion, the visible rise of invisible forces. Beneath the crust, entire continents are colliding, folding, and lifting each other skyward. The ground beneath the mountain is not still, it is exhaling. The process begins in silence, deep within the mantle where heat drives slow convection currents. These currents drag the tectonic plates like rafts of crust across the planet's molten underworld. Sometimes 2 plates meet head-on. When they do, neither surrenders easily. The lighter, buoyant crust crumples and thickens. Layers of rock stack and fold. Slabs slide over one another like waves frozen in time. In those immense grinding moments, mountains are born. The Himalayas are perhaps the most striking example, a range so vast it can be seen from space as a wrinkle on the face of the earth. They began when India, once an island continent, broke from Africa and drifted northward at the pace of a fingernail's growth, about 5 centimeters per year. After 40 million years of travel, it struck the southern edge of Asia with the slow inevitability of gravity itself. The collision has never stopped. Even now, each year, the peaks rise another few millimeters. Everest grows taller as rivers carve its valleys deeper. Creation and destruction occur together perfectly balanced. To grasp this, imagine time sped up 1,000-fold. The Himalayas would rise and erode like breathing inhale, exhale, rise, fall. The crust would ripple like cloth, the continents pulsing in and out. Mountains are not permanent monuments, but dynamic scars, records of ancient collisions that continue to shape the planet's face. Every mountain range has its ancestry written in folded stone. In the Alps, slabs of ocean floor are stranded atop limestone cliffs. In the Andes, volcanic peaks mark the boundary where the Nazca Plate slides beneath South America, melting rock into magma that feeds a chain of fiery summits. In the Appalachians, the ghosts of vanished continents still lie buried within the ridges, their story told through twisted seams of quartz and mica. To a geologist, each range is a living family tree, every layer a generation, every fault line a birthmark. But if uplift is the inhale, erosion is the exhale. The same forces that raise mountains also wear them down. Rain and wind, ice and gravity, all are agents of the planet's slow breathing out. A glacier gliding down a valley carries entire hillsides in its frozen grip. Rivers grind granite to sand and sand to dust. Even air, invisible and patient, eats away at stone grain by grain. Given enough time, every summit will crumble into the sea, becoming the sediment that will one day rise again as new peaks. This cycle, the mountain's breath, is endless. It keeps the planet's surface alive, reshaping continents, renewing ecosystems, redistributing minerals and nutrients. Without it, the world would be geologically dead, a smooth static sphere. Instead, we live on a planet that constantly remakes itself, one slow heartbeat at a time. Scientists can even measure this breathing. Using GPS satellites, they track how ranges like the Himalayas, the Andes and the Rockies move each year, lifting, bending and shifting by millimeters. During heavy monsoons or melting seasons, when billions of tons of water shift across the surface, mountains literally rebound as the weight changes. The crust flexes upward, then relaxes again like a chest filling and emptying. The Earth's surface is supple, alive, responding to every redistribution of mass. There's poetry in that motion. When you climb a mountain, you walk across something that is rising even as it erodes beneath your boots. You stand on a moment between two eternities, caught between the upward push of the deep earth and the downward pull of wind and water. Every ridge, every canyon, every fault line is a signature of balance. Even the smallest hills participate in this breathing. Beneath prairies and plains, old mountain roots lie buried, compressed under eons of sediment. Though invisible, they still respond to the planet's shifting weight. What looks like flat, stable land is simply the exhaled phase of an ancient upheaval, a place once high and proud, now resting before its next awakening. The breath of mountains also shapes life. As peaks rise, they alter wind and rainfall, creating deserts on one side and lush forests on the other. They trap glaciers that feed rivers, guide migration routes, and carve climates. Their erosion enriches soil with minerals. Entire civilizations are born and nourished in the spaces between these geologic inhales and exhales. And when the Earth finally grows quiet for a time, when continents drift apart and the crust steadies the mountains sleep. But even then, deep below, heat gathers currents, stir, and the cycle prepares to begin again. For every fallen range, a new one waits beneath, unseen, but inevitable. If you ever rest your hand on a rock wall, feel its coolness, its weight, its silence, know that it is moving. Know that it once flowed like wax, that it will one day flow again. Mountains may seem ancient beyond imagination, but they are as transient as waves caught in the long rhythm of the planet's breath. And in that rhythm, we live our entire lives, fleeting sparks upon the flank of something still rising, still exhaling, still alive. If you could watch the Earth's surface unfold over hundreds of millions of years, you would see a strange, beautiful dance, a ballet so slow that it looks still to the human eye, but one that never stops moving. Continents drift like dreamers across an unseen sea, their outlines changing, breaking, merging again. What seems to us like permanence is in the deep time of geology only a passing gesture in a vast choreography written by heat and gravity. Beneath the continents, the mantle moves. Though solid in form, it flows on a timescale of millennia, its currents driven by the heat that seeps outward from the core. Where the mantle rises, it pushes plates apart. Where it sinks, it drags them downward into the deep. The crust floats upon this convecting sea of stone light, and brittle, divided into giant slabs that fit together like pieces of a cracked shell. These are the tectonic plates, and their slow drift gives the Earth its ever-changing face. The first to glimpse this truth was Alfred Wegener, a German meteorologist who in 1912 dared to suggest that the continents move. He noticed how the coasts of Africa and South America seemed to match like two halves of a broken bowl. Fossils of identical plants and animals appeared on both sides of the Atlantic, separated by thousands of miles of ocean. To him, it was not coincidence, but evidence of a planet in motion. When Wegener proposed his idea of continental drift, the scientific world laughed. How could continents solid as stone drift like rafts across an ocean of rock? He had no mechanism to explain it, only the conviction that the Earth itself was alive with movement. He died before his idea was proven right. Decades later, as sonar mapping revealed the deep ridges and trenches of the seafloor, scientists discovered what Wegener could only imagine: a dynamic crust constantly being created and consumed, driven by the slow pulse of the mantle beneath. At mid-ocean ridges, new crust forms where molten rock wells up and cools, spreading the seabed apart like a zipper opening in stone. Elsewhere, at the edges of continents, the oceanic crust dives back down into the mantle, in long, dark trenches, melting and recycling itself in the planet's internal foundry. This is the cycle of renewal that keeps Earth's surface young, a moving belt of creation and destruction. Across hundreds of millions of years, this motion has drawn and redrawn the map of the world. Continents have collided and split apart, forming supercontinents, vast land masses, where all the Earth's continents once joined as one. The most famous of these was Pangaea, born roughly 335 million years ago. It stretched from pole to pole, a single immense body of land surrounded by an endless ocean called Panthalassa. In its center, deserts burned under the sun. Along its edges, storms brewed and seas churned. Life flourished, diversified, and spread across its continuous plains. But even Pangaea was only a phase in a much longer rhythm. Beneath it, the mantle's convection never stopped. The slow drift of heat and rock tore at its seams until around 175 million years ago, Pangaea began to break apart. Great rifts opened where molten rock rose, splitting the land into pieces that would become the continents we know today. As the Atlantic widened, the world took its familiar form, North America drifting westward, Africa pivoting East India racing north toward its collision with Asia. To imagine this movement, picture continents as passengers on a vast conveyor belt of stone. They travel at the speed your fingernails grow, about a few centimeters a year, but over time they cross oceans, rearrange climates, and reshape evolution itself. Mountains rise when they meet, oceans form when they part. Where plates slide past each other, earthquakes ripple like the planet's pulse. Where they diverge, magma blooms into new life, creating islands and seafloor. The continents are not inert, they are travelers. Some, like Australia, journey in solitude, drifting northward into new latitudes. Others, like Antarctica, remain anchored in icy stillness, though even its frozen shell glides slowly over the deep. Beneath the waves, entire microcontinents wander unnoticed, Madagascar, Zealandia, fragments of crust lost to time yet still moving. The drift is slow but unstoppable. Even now, scientists can predict the world millions of years into the future. Africa will eventually collide with Europe, closing the Mediterranean and raising new mountains where the sea once lay. The Americas will continue to drift westward. The Pacific will shrink until a new supercontinent forms a future Pangaea reborn under another name. The planet breathes in cycles of assembly and separation, each one lasting hundreds of millions of years. There is something profoundly humbling in this motion. Every border, every coastline, every familiar mountain range is temporary. The continents that cradle our civilizations are merely snapshots in a film that began long before us, and will continue long after. Yet without this drift, there would be no diversity of landscapes, no shifting of oceans, no renewal of life. The motion of the crust shapes not just geography, but the story of evolution and climate itself. In this slow dance of stone, time loses meaning. Mountains and oceans trade places, deserts bloom where glaciers once spread. Continents drift across climates like ships on a vast invisible tide. The planet's surface is not a map, it is a heartbeat, pulsing with heat from below. So the next time you look at a globe, remember it's not a picture of what Earth is, it is a single frame in a long film. The continents are still moving, still breathing, still tracing their quiet arcs across the molten mantle. You are living upon a traveller, one island of rock, adrift in the endless rhythm of the deep Earth's ballet. If the Earth were a book, its pages would never yellow with age. They would rewrite themselves, endlessly old words melting into new ancient chapters, erased by heat and written again in fire and stone. That is what plate tectonics truly is, a planetary recycling system, a slow miracle that keeps the world forever young. Look beneath the illusion of stillness, and you'll find a rhythm that has never ceased since the planet's birth. New crust is constantly being born at the mid-ocean ridges, those long underwater mountain chains that run like stitches across the seafloor. Here, molten rock rises from the mantle, cools in the icy water, and hardens into new basalt. As more magma wells up, the newborn crust is slowly pushed aside inch by inch, creating vast plains of ocean floor that drift outward like conveyor belts of stone. But nothing on Earth lasts forever, not even rock. At the far edges of the oceans where plates collide, that same crust bends downward into the deep, disappearing into trenches that carve the planet's surface into shadows. This is subduction, the quiet devouring that balances creation. As the old crust sinks, it melts again into magma, returning to the mantle it came from. The cycle closes. From molten birth to stony life to molten death, the crust is renewed. You can see the proof of this eternal circulation in the age of the seafloor itself. The crust nearest the ridges is young, barely a few million years old. But the farther you go from the ridge, the older it becomes until it vanishes entirely in a subduction zone. Unlike the ancient continental crust, which can survive for billions of years, oceanic crust is fleeting, reborn every 200 million. In the time it takes for one supercontinent to form and break apart, the entire ocean floor has been replaced. This constant renewal is why Earth's surface remains so dynamic. On worlds like Mars or the Moon, where tectonic motion has long since stopped, the crust grows old. Craters remain frozen for eons, mountains crumble, but are never rebuilt. Their landscapes are the scars of a youth that ended billions of years ago. But Earth is different. Here destruction is creation's twin. Erosion, volcanism, and plate motion continually reshape the world, erasing its wounds and keeping it alive. It is a paradox of geology. The very instability that makes the planet unpredictable is what keeps it fertile. The subduction zones that swallow crust also pull water deep into the mantle, where it lowers the melting point of rock and fuels new volcanoes. Those volcanoes in turn release gases that replenish the atmosphere and minerals that nourish the oceans. Without subduction, without this slow churning of stone and water, the Earth would lose its breath. The air you inhale, the soil that grows your food, the continents themselves, all are the products of this hidden renewal. Picture the Pacific Ring of Fire, where the crust dives beneath continents, in a ring of volcanoes that circle the ocean. Japan, the Andes, the Cascades, New Zealand, all of them are children of subduction. Beneath their mountains, slabs of old ocean floor are melting away, fueling the eruptions that build new land. From destruction rises creation lava, cooling into fertile soil, ash feeding forests, minerals sparking life in deep-sea vents. Even continents, seemingly eternal, owe their existence to this cycle. When plates collide, fragments of ocean crust and island arcs are scraped off and welded onto the edges of land masses. Over time, these accreted pieces build up continents layer by layer like coral reefs of stone. Look at a world map and you can see their scarce chains of mountains and islands, tracing the boundaries of ancient collisions. The continents are mosaics of survival, each grain of sand a relic of subduction past. If the Earth could speak, it might describe this process as breathing an inhale of creation at the ridges and exhale of consumption at the trenches. It is a rhythm of balance, keeping the planet's heat in motion, its surface renewed, its spirit young, and within that balance lies life's greatest fortune. Because the crust is recycled, the climate stabilizes. Carbon locked in rocks is released through volcanoes, then drawn back into stone through weathering and burial. This carbon cycle, a geologic heartbeat, has kept Earth's temperature within the narrow window that allows oceans to remain liquid and life to persist. Without tectonics, there would be no moderation, no self-correction, no second chances. The planet would either freeze into stillness or burn itself dry. Instead, it remains alive, endlessly reinventing itself. Every mountain once lay beneath the sea. Every grain of sand was once part of a volcano. Every continent was once ash and magma melted and reformed. The solid ground beneath your feet is the product of countless deaths and rebirths. This cycle also carries a subtle poetry. The same mantle that swallows crust at one boundary gives birth to it at another, as if the planet refuses to let any part of itself truly die. The oldest ocean floor sinks and the youngest rises, renewal by fire, burial by water, resurrection by pressure. Over billions of years, this rhythm has erased entire worlds and built new ones in their place, each more complex than the last. The Earth then is not just a planet, it is a process. It does not grow old because it never stops moving, never stops consuming and creating itself. The continents may drift, the oceans may vanish, but the cycle continues transforming what was into what will be. If you close your eyes tonight and imagine the ground beneath you, don't see it as fixed stone. See it as motion slowed to stillness, as molten memory given form. Somewhere below rock is melting, new crust is forming, and the earth is quietly turning itself over, renewing, rebalancing, breathing. The world you walk upon is ancient, but it has never truly aged. It is in every sense alive. Stand before the Himalayas and you're standing in the middle of a collision that has never ended. Their peaks pierce the jet stream white, as bone-cold as silence, and yet they are not fossils of a bygone world, they are in motion. Every ridge, every valley, every trembling fault is part of an unfinished sentence written by the Earth's own hands. The Himalayas are still rising day by day, grain by grain, as the planet continues to shape itself from within. 50 million years ago, the story began with a slow, unstoppable journey. The land that would become India was once an island adrift in the ancient Tethys Sea, far to the south of Asia. After breaking away from the supercontinent Gondwana, it drifted northward across the equator at nearly 15 centimeters a year, a reckless pace for a continent. Ahead of it lay Eurasia, immense and unmoving. Between them, the ocean floor sank and folded until at last the two collided. When India struck Asia, it did not stop. The ocean between them vanished, squeezed upward into rock and mountain. The sediments that once lay beneath the Tethys Sea rose into the thin air to form the roof of the world. And because the engine beneath the convection of the mantle kept pushing, the mountains never settled. To this day, the Indian plate continues to dive beneath the Himalayas, crumpling the crust like paper under invisible hands. The result is uplift, slow, steady, unstoppable. Measured by satellite, the Himalayas rise an average of 5 millimeters a year, about the rate your fingernails grow. It seems nothing, yet over geological time it reshapes the planet. In the span of a human lifetime, the mountains may rise only the thickness of a coin, but in a million years they will tower hundreds of meters higher. The air that feels eternal is in fact thinning a little more each day as stone ascends toward the stratosphere. Earthquakes are the mountain's heartbeat, the tiny violent whispers of ongoing creation. Each tremor marks a sudden slip in the vast grinding contact zone between the Indian and Eurasian plates. When stress builds beyond the strength of rock, it releases in a burst of motion, shaking valleys, toppling walls, and shifting the landscape by centimeters in seconds. The devastation we feel on the surface is the sound of the earth adjusting to its own architecture. It is not chaos, it is maintenance. Some of these quakes are enormous. In 2015, a rupture beneath Nepal released centuries of pent-up strain, moving parts of the country several meters southward and lowering Mount Everest by nearly an inch. Yet even that colossal event was only a breath in the mountain's long life. The plates locked again, the pressure began to rebuild, and the slow rise resumed. The Himalayas are both builders and destroyers, carving and uplifting in the same motion, sculpting a world that will never be finished. The mountain range stretches 400 kilometers across the planet's roof, from the arid spurs of Pakistan to the humid foothills of Myanmar. It includes not only Everest, but hundreds of peaks higher than any outside the range. Beneath their summits, entire ecosystems depend on the uplift glaciers that feed the Ganges, Indus, Yangtze, and Mekong rivers that sustain nearly 2 billion lives. Without the Himalayas breathing upward, Asia's great waters would dry, and the monsoon winds that shape the continent would lose their rhythm. But the Himalayas are more than geology. They are a dialogue between earth and sky. The crust presses upward, and the atmosphere answers. As the mountains rise, they draw clouds, redirect jet streams, and trap cold air in their valleys. Snow falls, glaciers grow, and the weight of ice presses back against the rising rock. The planet adjusts itself with exquisite precision, gravity balancing uplift, erosion countering, elevation temperature moderating force. It is a choreography between stone and weather written in frost and fault lines. Even erosion, the mountain's slow undoing, is part of its renewal. Rivers born from glaciers carry away the very sediments that once formed the seafloor, scattering them across the Indo-Gangetic plain. There they nourish fields, cities, and forests. The soil beneath Delhi, Lahore, and Dhaka is ground-up Himalayan memory, a gift from peaks that rise by crumbling. What falls becomes fertile, what erodes feeds life. To the human eye, the Himalayas seem beyond comprehension, ancient, immovable, immortal. Yet under satellite watch they reveal their pulse. GPS sensors anchored into bedrock shift each year. Valleys widen, fault lines creep, new lakes form behind glacial dams. The Earth is still writing here, and the story is ongoing. What we call mountain is merely a frame of the planet mid-sentence. Even the air remembers. As the mountains rise, the climate changes, glaciers expand and retreat, species migrate upward, and the monsoon adapts to the new altitude. The Himalayas have become an evolutionary forge testing life against thin air and cold light. Snow leopards, yak rhododendron, and monks in high monasteries all are part of the same experiment in endurance. Someday, perhaps tens of millions of years from now, the motion will slow, the plates will find equilibrium, the peaks will stop rising, and erosion will finally win. The Himalayas will flatten into plains and new mountains will rise elsewhere, but that time is far beyond our horizon. For now, the collision continues, a deep, slow heartbeat, echoing beneath the snow. When you look at Everest, think of what lies beneath not stillness, but a continent still crashing into another. Think of each tremor as a breath, each crack as a sigh. The Himalayas are not ruins of creation, they are its continuation. They are the living proof that the earth is never finished, that even stone given enough time can move like wind. And so the mountains breathe on, lifting skyward inch by inch, while rivers carve them down, while life adapts, while the planet reshapes itself in its endless conversation of fire pressure and time. If you were to mark a mountain peak on a map and return a century later, it would not be in the same place. It would have drifted perhaps only a few meters, imperceptible to any human eye, but real. Continents move at the pace of hair growth 2, sometimes 5 centimeters a year. Yet given enough time, this barely measurable crawl rearranges the entire world. Oceans open and close, deserts bloom and vanish. Species migrate, climates transform. What we call geography is simply slow motion caught in mid-frame. Imagine the Earth viewed through a million-year time-lapse. The continents slide and twist like slow clouds over a glowing sea of mantle. Africa drifts northward toward Europe. Australia glides into the tropics. North and South America drift west, stretching the Atlantic ever wider. Ice caps form and melt as latitudes shift. Archipelagos rise and drown. A single millimeter each month becomes over eons, the difference between mountain and plain, between frozen tundra and fertile valley. The secret lies in the restlessness beneath. Heat from the planet's core rises through the mantle in sluggish convection currents, dragging the crust along with it. The plates ride those currents as if on invisible conveyor belts. Where the currents diverge, new crust forms. Where they converge, it is swallowed back into the deep. It is a circulation so slow that human lifetimes cannot register it, but so steady that it has rewritten the Earth's map 1,000 times. Scientists once struggled to believe in such glacial motion. How could continents drift without tearing apart? The proof came not from sight, but from magnetism. As lava cools at the mid-ocean ridges, iron minerals align with the planet's magnetic field like millions of tiny compass needles. Each stripe of basalt on the ocean floor preserves the direction of Earth's magnetic north at the time of its birth. When researchers mapped those stripes, they found symmetrical patterns on both sides of the ridges, evidence that new crust had indeed been spreading slowly but relentlessly for tens of millions of years. From this tiny motion flow consequences far greater than scale suggests. When continents move, they carry life with them. 45 million years ago, as Australia drifted away from Antarctica and into warmer latitudes, its ecosystems exploded with diversity: marsupials, parrots, eucalyptus. India's collision with Asia not only raised the Himalayas, but altered the entire global climate, trapping monsoon systems and reshaping ocean currents. Even the cooling of the planet over the past 30 million years owes part of its rhythm to this slow rearrangement of land and sea. 2 centimeters a year, so little yet so decisive. It shifts wind patterns, redirects ocean circulation, and determines where life can thrive. When South America joined North America 3 million years ago, closing the Isthmus of Panama, it cut off the exchange between the Pacific and Atlantic Oceans. The result was the strengthening of the Gulf Stream, a warmer North Atlantic, and perhaps even the glaciation of the Arctic. A bridge of land only a few hundred kilometers wide rewrote the planet's climate. Humanity, though new to the story, lives upon this moving stage. The ground beneath our cities is not still. It glides upon a sea of stone. Satellites now measure the drift with exquisite precision. They tell us that Los Angeles creeps north toward San Francisco, that Africa inches toward Europe, that the Atlantic expands by the width of your thumb each year. We are passengers on a ship so vast we cannot feel its motion, yet its voyage will one day transform every coastline. This slow drift gives time its tangible shape. The continents we recognize today, Africa's curve, South America's taper, Asia's immensity, are merely a temporary arrangement. 200 million years from now, the globe will look unrecognizable. The Mediterranean will close. The Americas may fuse with Asia. A new supercontinent, perhaps Amasia, will rise where the Arctic now lies. The Earth does not keep still. It edits itself continuously. There is humility in that knowledge. Mountains rise and erode, oceans spread and vanish, climates cool and warm, yet all of it stems from a motion smaller than the growth of your hair. The power of the planet resides not in speed, but in persistence. With patience, even the tiniest movement can sculpt worlds. If you could rest your ear to the ground and listen for long enough, you might hear the faintest murmur of that motion, the deep, slow hum of rock against rock, the planet's heartbeat stretched across epochs. Every second that passes, continents glide a fraction farther, and the world you know becomes something new imperceptibly but certainly. In the quiet of deep time, centimeters become oceans. The Earth, ever patient, keeps moving, and you, standing still upon it, are already travelling. Beneath the calm surface of the seas, the Earth is busy building new worlds. Deep under the water in darkness, broken only by the faint shimmer of molten light, the planet is giving birth to new crust. The process is constant, methodical and ancient, yet the results are always young. Every square metre of ocean floor you have ever crossed in a ship or seen on a map is, by geological standards, a child. While the continents carry memories billions of years old, the seafloor is reborn every few hundred million years. It is the planet's most active frontier, a realm where stone is still warm from creation. At the centre of nearly every ocean lies a scar, an immense ridge that snakes across the planet like a seam on a baseball. These mid-ocean ridges stretch for over 65,000 kilometres, forming the longest mountain range on Earth, though almost none of it rises above the waves. Here the crust splits apart as molten rock wells upward from the mantle, cools and hardens into new basalt. Slowly the two sides of the ridge drift away, carrying the fresh crust outward like pages turning in a book that never ends. This is seafloor, spreading the invisible expansion that continuously renews the face of the oceans. If you could drain the Atlantic dry, you would see this process in motion. Along its centre runs the Mid-Atlantic Ridge, a vast volcanic rift valley where magma glows beneath thin crust, creating new seafloor every day. The ridge rises like a spine from the deep, dotted with hydrothermal vents, geysers that spew mineral-rich water, hotter than boiling point feeding ecosystems that exist without sunlight. Around these black smokers, life thrives on chemistry alone, drawing energy from the planet's heat rather than from the sun. The ridge is both cradle and furnace, a reminder that life and geology are two faces of the same motion. The crust formed here spreads outward at only a few centimeters per year, no faster than your nails grow, but its persistence is endless. As it cools and moves away from the ridge, it thickens and sinks, becoming denser, until it finally meets the edge of another plate. There in deep ocean trenches, the oldest crust is forced downward into the mantle, melted and remade. It is a perfect cycle: birth at the ridge, death at the trench, renewal through fire. That is why the ocean floor never grows old. The Atlantic's oldest rocks are barely 180 million years old, youthful, compared to the continents, where ancient granites have endured for more than 4 billion. The seafloor records its own history like the rings of a tree. As molten basalt emerges and cools, iron minerals inside it align with the planet's magnetic field. Over time, as Earth's magnetic poles flip, these minerals form symmetrical stripes of reversed magnetism on either side of the ridge. Scientists studying those patterns in the 1960s realized what Alfred Wegener had once guessed: the continents move, carried along by the slow spread of the seafloor. The ridges are the engines of drift, the birthplace of motion. Each ridge is unique. The East Pacific rise is fast and smooth, its crust spreading more than 10 centimeters a year, one of the fastest geological processes on the planet. The Mid-Atlantic Ridge, slower and more rugged, builds deep rift valleys that slice the ocean floor like scars. In the Indian Ocean, 3 ridges meet at a triple junction, a place where the world's plates pull apart in 3 directions at once. From these hidden boundaries, new worlds are continuously stitched into being. The youth of the oceans gives them their beauty and their restlessness. The crust beneath the seas is thin, barely 7 kilometers thick on average, compared to the continent's 40. It is denser, darker, and more fragile, prone to cracking and trembling as the mantle stirs beneath it. Earthquakes ripple along its faults. Volcanoes rise in long chains called seamounts, each marking a place where the crust gave way to molten breath. Over time, some of these volcanoes grow tall enough to breach the surface, becoming islands. Hawaii, Iceland, the Azores, all children of the ridges or of the plumes that burn through their thin skin. This youth also explains why the ocean floor is smooth, why it lacks the deep scars of ancient craters that mark the Moon or Mars. Those worlds are geologically quiet. Their wounds never heal. Earth, by contrast, is in constant renewal. Every few 100 million years, the planet turns its seafloor inside out, erasing its own past. What falls into the trenches melts into new magma. What emerges at the ridges becomes the next generation of stone. Even the deepest abyss is temporary, a moment between creation and return. And yet in this restless system lies balance. The spreading ridges that birth new crust are offset by the subduction zones that consume it. If the crust were created without destruction, the planet would swell endlessly, its oceans spilling over continents. If it were destroyed without renewal, the seas would shrink and vanish. Instead, creation and consumption proceed in harmony, keeping the planet's size constant while its surface evolves. The Earth remains young because it never stops rebuilding itself. When you look out over the ocean, you're gazing at the youngest part of the planet's skin. Beneath the waves, new rock is forming, even now unseen, hot enough to glow delicate enough that it will one day sink and start again. The continents are the elders of the Earth, scarred, patient, filled with memory, but the oceans are its children eternally reborn in the dark. Somewhere in the black silence of the deep, a vent exhales its mineral breath, and the planet writes another line in its endless autobiography of renewal. The young oceans are proof that even in darkness, creation never ceases. There is a hidden memory written into the floor of the oceans, a code so vast and subtle that no human eye could see it until machines began to listen. It lies in stripes, thousands of kilometers long, running parallel to the great mid-ocean ridges. To a casual glance, the seafloor seems uniform, dark basalt, cold and silent, but to a magnetometer it hums with history. The planet's magnetic field, ever shifting and mysterious, has left its signature there, frozen into stone. And it was this quiet memory, the magnetic barcode of the seas, that finally revealed how the Earth truly moves. The story begins with the planet's molten heart. Deep within the core, liquid iron swirls in convection currents, generating the geomagnetic field, a colossal, invisible shield that deflects solar wind and guides compass needles toward what we call north. But north is not constant. Throughout Earth's history, the magnetic poles have reversed hundreds of times. What is north today was south millions of years ago and will be again. Each reversal is unpredictable, taking thousands of years to complete, like the slow turning of a planetary hourglass. When molten rock emerges along a mid-ocean ridge, it carries this magnetic field within it. As it cools, the iron-rich minerals, tiny crystals of magnetite, align themselves with the direction of the field, just as iron filings align around a bar magnet. In that moment, the rock records the planet's magnetic orientation, locking in a memory of north that will remain until the stone melts again. Now, imagine the ridge as a giant conveyor belt, endlessly creating new seafloor and pushing it away on both sides. Every time the Earth's magnetic field flips, the next stretch of rock forms with its magnetic direction reversed. Over millions of years, this process paints symmetrical stripes of normal and reversed polarity. On either side of the ridge, a geological barcode that records the rhythm of the planet's magnetic heartbeat. In the early 1960s, when scientists towed magnetometers across the Atlantic and Pacific, they discovered these stripes for the first time. The instruments traced a pattern so regular, it seemed almost artificial, alternating bands of positive and negative magnetic readings perfectly mirrored across the ridges. It was as though the seafloor itself had been magnetically printed. Each stripe represented a period between pole reversals, its width reflecting how fast the crust was spreading at that time. Together they formed a chronological record stretching back tens of millions of years. The revelation was revolutionary. Until then, Alfred Wegener's theory of continental drift had remained controversial, a poetic idea without a mechanism. But now the evidence was etched into the planet itself. The ocean floor was not static. It was moving, growing from a central spine and carrying the continents with it. The magnetic striping provided irrefutable proof that plate tectonics was real, the long-missing link between observation and explanation. What astonished scientists even more was the precision of this natural record. By comparing the magnetic polarity of the seafloor with known reversals preserved in volcanic rocks on land, they could calculate spreading rates and reconstruct the movement of continents with remarkable accuracy. In some regions, the crust spreads as slowly as 2 centimeters per year, in others as fast as 20. Each stripe is a frozen year in the life of the planet, each ridge a pulse of creation. To read the magnetic memory of the seas is to hold a timepiece older than civilization. You can trace the widening of the Atlantic since its birth, follow the journey of Africa away from South America, or watch the Pacific slowly shrink beneath its fiery ring of subduction zones. These are not metaphors, they are measurements precise and tangible. What was once theory has become map, what was mystery has become rhythm. Even today, the Earth continues to write new stripes. Every second, somewhere along a ridge, magma wells up, cools and locks in a snapshot of the magnetic field as it stands right now. When the next reversal comes, and it will, the pattern will change again, marking a new chapter in the story of the planet's restless heart. The idea that solid stone can carry memory feels almost mystical, but it is grounded in physics. The magnetite crystals in basalt are minuscule, yet perfectly obedient to the field they cool within. Together, billions of them preserve a collective direction, like a choir holding a single note for eternity. That note, inaudible to our senses, is what magnetometers detect the faint hum of ancient norths and souths layered across the ocean floor. Every reversal of the magnetic field reminds us of the planet's duality stability, born of constant motion. Even the poles wander slowly now, drifting tens of kilometers each year. The field weakens, strengthens, bends. But the rocks remember every change, patient and exact. When we map their magnetism, we are not simply studying the past, we are eavesdropping on the Earth's memory of itself. So next time you look at a map of the oceans, imagine beneath those blue depths, a vast record player inscribing the music of magnetism into stone. The continents glide across it unaware, like dancers following a beat too slow for the human ear. And beneath them, the seafloor continues to hum its secret song, an ancient melody of reversal, renewal, and drift. The magnetic memory of the seas is proof that even silence can speak, that the Earth in its quietest depths never stops telling its story. If you hold a small piece of volcanic rock in your hand, it seems utterly silent, just a rough, cold fragment of the Earth. But inside it, billions of microscopic compass needles are frozen in perfect alignment, each one pointing toward a north that may no longer exist. These tiny grains of magnetite and hematite, born from cooling lava, are the planet's invisible historians. They remember the direction of Earth's magnetic field at the very instant they solidified tiny archives of planetary motion carried within what appears to be lifeless stone. When molten rock erupts from a volcano or seeps across the ocean floor, it begins as liquid chaos atoms, whirling bonds, breaking temperatures high enough to melt steel. But as it cools, order begins to form. Iron-bearing minerals crystallize out of the magma, and in those fleeting moments, before they harden completely, the magnetic field of the planet imprints upon them. The particles align themselves to magnetic north like millions of invisible compass needles, and once the rock solidifies, their directions are locked in place. That magnetic orientation can endure for hundreds of millions of years long, after mountains rise and erode, long after the continents drift into new configurations. These rocks form the basis of a science called paleomagnetism, the study of ancient magnetic fields preserved in minerals. It was paleomagnetism that gave humanity its first real proof that continents move. In the mid-20th century, researchers noticed that rocks of the same age on different continents recorded magnetic poles in completely different places. The simplest explanation was not that the magnetic field had gone wild, but that the continents themselves had shifted positions. The stones were right. It was our assumptions that were still. Earth's magnetic poles are restless. Even when they are not flipping entirely as they do every few 100,000 years, they wander. At this very moment, the North Magnetic Pole is racing across the Arctic Ocean towards Siberia at more than 30 kilometers per year. The South Pole drifts too, but at a gentler pace. These changes come from the ceaseless movement of molten iron in the planet's outer core, a churning ocean of metal, 2,000 kilometers thick, that acts as a colossal dynamo. The currents there generate electrical and magnetic fields that stretch through the entire planet and even far into space, shielding life from the charged particles of the solar wind. When the magnetic field weakens or shifts, the rocks take note. Each lava flow, each volcanic eruption, each layer of seafloor basalt quietly records the field's current direction and strength. Geologists collect these samples from across the world: volcanoes in Iceland, layered basalt cliffs in India, and ancient lava flows frozen beneath the ocean, to reconstruct the slow waltz of the poles over time. By comparing thousands of samples, they can trace how magnetic north has wandered across the globe like a slow, uncertain traveller. Sometimes the record is startling. Lava flows stacked one atop another in long-dormant volcanoes reveal entire sequences of reversal, where the field faded, flickered and returned, pointing south instead of north. In such rocks, the invisible compasses literally turn upside down within layers only meters apart, showing that the change unfolded over just a few thousand years, a blink in geological time. To the creatures living then, the sky would have looked the same. The magnetic field is invisible. But to the stones beneath their feet, a new story had already begun. The drifting of the magnetic poles leaves its fingerprints everywhere. Ancient lava in North America tells of a time when the poles sat in the middle of the Pacific. European rocks show it once wandered near Africa. By aligning these records with the modern positions of the continents, scientists have charted their long migrations with astonishing precision. The rocks, in essence, have been taking notes for billions of years, and together they tell a consistent tale. Continents drift, poles wander, and the planet never stops moving. Even now, new magnetic memories are being written. Each eruption adds a fresh layer to the global archive. Each spreading ridge prints a stripe of polarity across the seafloor. The magnetism within those stones may one day guide future civilizations to understand where we stood just as we use them to glimpse the Earth's past. There's a quiet poetry in this process, molten fire cooling into ordered memory. The same iron that burns red in blood also whispers direction to stone. It is one of the universe's subtler miracles that the same element that allows life to carry oxygen also allows the planet to remember its breath. So when you pick up a piece of volcanic rock, remember what it holds. Within that small dark weight lies a frozen echo of the Earth's invisible field, the steady heartbeat of a molten core that never sleeps. It points toward a north that may have been, or one still yet to come, a compass written not for travelers but for time itself. Every volcano on Earth has a pulse. Most of the time it beats quietly deep beneath mountains, forests or tranquil seas, slow, steady and unseen. Only when pressure rises does the planet's heartbeat quicken its rhythm, shifting from silence to fury. What we call an eruption is not a sudden act of violence, but the release of a long and patient breath exhaled from the molten heart of the world. Far below the surface, magma moves through the crust like blood through arteries. It gathers in chambers vast reservoirs of molten and partially molten rock fed from the deeper mantle by narrow conduits that glow with heat. These chambers vary in shape and size, some are small and shallow, lying only a few kilometers beneath the surface. Others are immense systems extending for tens of kilometers, downward branching like roots. Inside them, crystals form and gases rise, pressure builds and subsides. It is a cycle of accumulation and release that can last centuries. Modern science has learned to hear these hidden hearts beating. Using seismic imaging, scientists send vibrations through the crust and listen for echoes that reveal what lies below. Because molten rock slows and bends sound waves, it shows up as bright fluid regions on their maps, warm colors in a portrait of the planet's interior. With this ultrasound of the Earth, geologists can now visualize magma chambers tracing their outlines and watching them expand or contract. Beneath Yellowstone, for instance, the main magma body stretches for over 90 kilometers, like a sleeping dragon beneath fields of geysers and pine. Sometimes these chambers swell imperceptibly, lifting the ground above by mere millimeters each year. Other times, inflation accelerates, signaling that new magma is rising. Satellites orbiting hundreds of kilometers above can detect these changes with astonishing precision. The Earth's skin flexes, its pulse quickens, yet not every rise ends in eruption. Volcanoes breathe, they inhale magma and exhale gas. When gases find pathways to escape pressure, eases and the volcano returns to dormancy, its cycle unbroken. Inside a magma chamber, conditions are otherworldly. Temperatures can exceed 200 angst. Pressures reach tens of thousands of atmospheres. Crystals float in molten rock like stars in a glowing nebula. Bubbles of water vapor and carbon dioxide gather, trapped until they can find release. Over years, these bubbles accumulate and coalesce. When they finally burst free, the result is a violent decompression, lava fountains, ash clouds, pyroclastic flows. The heartbeat that had been steady and deep suddenly surges into the open air. Yet even in eruption, the volcano follows a rhythm. The explosive outburst is often followed by long periods of quiet degassing, then gradual rebuilding. Lava refills emptied conduits, gases seep upward, and the cycle begins anew. A single volcano may undergo this pattern dozens of times across millennia. Mount Etna, one of Earth's most studied volcanoes, has erupted regularly for 500,000 years. It breathes not in minutes or hours, but in epochs. For the people who live near them, volcanoes are both threat and benefactor. The same eruptions that devastate can also create their ash, enriches soils, their heat powers geysers, their eruptions birth new land. The magma chambers beneath them are not malevolent furnaces, but part of a planetary circulation system. Through them, the Earth releases internal heat and renews its surface. In a sense, volcanoes are the planet's lungs where pressure finds balance, and the interior meets the open sky. Listening to a volcano's heartbeat has become a science of patience and respect. Networks of seismographs detect the tremors that precede eruptions, while gas sensors track the chemistry of escaping fumes sulfur, carbon, chlorine. Satellites measure ground deformation, and drones skim ash plumes to sample their composition. Together, these tools create an orchestra of data that scientists interpret like a stethoscope pressed against the chest of the Earth. Each volcano has its own rhythm, its own song of pressure and release. Sometimes that rhythm grows erratic. The ground trembles with harmonic tremors, low continuous vibrations that rise like the deep hum of a cello. Magma is moving, gases escaping faster. The pulse quickens. Minutes, hours, or months later, the mountain exhales in flame. The eruption itself is the planet's heartbeat, made visible, a reminder that beneath every valley and meadow, the Earth is still alive with motion and heat. But even when all is quiet, when no ash clouds billow, when the slopes are green and peaceful, the heart still beats below. Seismic instruments detect faint tremors, micro-earthquakes that come and go like breaths. The volcano sleeps, but its dreams are warm and bright, filled with slow rivers of molten rock winding through black chambers. If you could stand above one of these sleeping giants and listen closely, not with your ears, but with time, you might hear that deep, patient rhythm. The rise and fall of pressure, the flow and stillness of molten stone, a pulse measured not in seconds, but in centuries. The volcano's heartbeat is the Earth reminding itself to breathe, and every eruption, every plume of ash or river of lava is just one moment in that endless cycle of exhalation, heat returning to skystone, returning to dust, the planet's inner fire, whispering once more to the surface, I am still alive. There are eruptions, and then there are cataclysms so vast that they seem to belong to another world. Imagine fire not as a column from a single mountain, but as an ocean. Imagine the ground itself opening for thousands of kilometers, and from those wounds, rivers of molten rock pouring out not for days or years, but for hundreds of thousands of years. These were the flood basalts, the planet's greatest exhalations, when Earth's crust seemed to melt from beneath, and the world's breath turned to flame. The Deccan Traps of India, the Siberian Traps of Russia, the Columbia Plateau in North America, these are scars of such events. The word traps comes from the Swedish trapper, meaning stairs, describing the step-like layers of solidified lava that still cover the landscape. In some places they rise over 2 kilometers thick, a monument to eruptions that dwarfed anything humanity has ever witnessed. A flood basalt begins far deeper than an ordinary volcano in the mantle itself. Their immense plumes of molten rock rise like slow tornadoes of heat, spreading outward when they strike the base of the crust. The pressure fractures the surface, opening great fissures tens of kilometers long. Through them, magma gushes forth, not explosive like Mount St. Helens or Vesuvius, but relentless. Each flow can stretch for hundreds of kilometers, moving like glowing rivers that bury valleys and mountains alike. In the case of the Siberian Traps about 252 million years ago, the outpouring lasted close to 1 million years. Over that span, more than 3 million cubic kilometers of lava flooded the surface, enough to bury the entire continental United States under a mile of basalt. As the molten rock spread, it ignited thick beds of coal and organic sediments, releasing vast amounts of carbon dioxide, methane, and sulfur gases into the air. The sky darkened, acid rain fell, the oceans turned warm and anoxic. It was not merely a geological event, it was a planetary fever. The Earth's greatest mass extinction followed over 90% of marine species, and 70% of land life vanished. The Permian world ended not with an asteroid's impact, but with a slow, suffocating fire from within. A similar story unfolded 66 million years ago, with the Deccan Traps in what is now Western India. For nearly 1 million years, magma poured from fissures stretching hundreds of kilometers, covering an area larger than France. Each eruption released billions of tons of gas, transforming the atmosphere. The skies filled with aerosols that dimmed sunlight, cooling the planet at first, then as carbon dioxide accumulated, warming it catastrophically. Forests died, oceans acidified, ecosystems collapsed. The Earth's thermostat lurched from one extreme to another. At almost the same moment, a massive asteroid struck the Yucatan Peninsula. Debate still lingers over how much each event contributed to the extinction of the dinosaurs, but most scientists now believe the two disasters overlapped their effects, amplifying one another. The impact may have triggered volcanic pulses in India. The volcanoes in turn prolonged the climatic chaos that followed. The result was a world emptied of giants, clearing the stage for mammals, and eventually humans to rise. To visualize a flood basalt is to imagine the Earth turning itself inside out. Lava curtains tens of meters high spill from fissures glowing orange against a blackened sky. The air trembles with heat. As the flows spread, they form plateaus of molten rock that stretch beyond the horizon, cooling into hard basalt crusts that crack and steam. With each eruption, gases surge into the stratosphere, sulfur creating veils of reflective haze, carbon dioxide building invisible blankets of warmth. The planet swings wildly between cold and heat, between darkness and fire. Even after the eruptions cease, their influence endures for millions of years. The basalt plains weather, slowly drawing carbon dioxide from the air and stabilizing the climate once again. Life returns, altered but resilient. New species evolve to fill the emptied niches. The very catastrophe that destroys one age becomes the soil of another. The flood basalts are both executioners and midwives, endings and beginnings written in stone. Today, the remnants of those fiery epochs still shape continents. The Deccan Traps form a rugged plateau where fertile black soils now nourish India's farmlands. The Columbia River basalt group underlies vast regions of the Pacific Northwest, its cliffs carved by ancient floods into cathedral walls. The Siberian Traps stretch across millions of square kilometers of frozen tundra, their stair-stepped ridges still whispering the memory of fire. In the grand timescale of the planet, these events are rare, perhaps a dozen in the last 500 million years, but their fingerprints are unmistakable. They remind us that Earth's surface calm is only an interlude, that beneath the continents the mantle still roils, capable of unmaking and remaking the world. The same process that built the crust can, when unrestrained, drown it. And yet from those floods of fire, something enduring emerges: balance. The Earth's systems, thrown into chaos, eventually restore themselves. The gases disperse the rocks, weather the air clears. What was devastation becomes renewal. Without these fiery purges, the planet might never have evolved the diversity it carries now. If you walk the black basalt steppes of the Deccan, or stand upon the windswept ridges of Siberia, you're walking on the cooled breath of the Earth itself. Each layer beneath your feet was once a river of flame. Each horizon tells of a time when the planet burned, and from that burning began again. The world remembers in stone, and stone remembers the fire. Far below the glittering surface of the sea, sunlight fades to twilight, then to black. Pressure builds until even sound feels slower, heavier drawn out. Yet in that silent dark, the Earth is still building. Here along the endless scars of the mid-ocean, ridges molten rock rises from the planet's interior and meets the deep cold of the ocean. What happens next is one of nature's quietest miracles, the creation of the planet's dark armor, the basaltic crust that covers more than 2/3 of Earth's surface. The seafloor may look smooth in maps, but in reality it is an intricate mosaic of creation. When magma seeps from cracks at the spreading ridges, it cools so fast that it cannot form crystals. The outer surface freezes instantly while the interior remains molten and fluid, pushing outward until the thin shell cracks again and again. Each new burst creates a round, bulbous shape, a pillow lava like a stack of stone bubbles. Together, these forms pile upon one another layer after layer until the ocean floor resembles a frozen sea of ripples, as if the rock itself had once flowed like water. These pillows are more than just shapes. They are a record of the conversation between fire and water. At the moment molten basalt touches seawater, temperatures differ by nearly 1,000 degrees. The water flashes into steam, cooling the lava's surface into glass so quickly that even gas bubbles are trapped within. In cross-section, you can see them, small vesicles, tiny fossils of breath preserved in stone. Each one marks a heartbeat of eruption, each pillow a phrase in the language of heat meeting cold. Over time, these pillows merge and fracture, forming the uppermost layer of the oceanic crust. Beneath them lies a denser zone of basaltic sheet flows, massive ropey plains that stretch for kilometers, and below that thick layers of gabbro where magma once cooled more slowly in the depths. Together these layers make up the oceanic lithosphere, the planet's hard shell beneath the seas. From the surface of a satellite it seems inert, but up close it is alive with texture, motion, and quiet artistry like cooled ink frozen mid-splash. When scientists first dredged samples of pillow lavas from the ocean floor in the mid-20th century, they were astonished at their perfection. Each pillow was distinct, yet part of a whole connected by thin, glassy skins and cooled edges that still shimmered under light. Some bore delicate flow lines where the lava had stretched before freezing like brushstrokes on a sculpture. Others held tiny tubular cavities where superheated water once hissed outward. To geologists, these forms were both data and poetry, a physical signature of the newborn crust's rapid birth beneath crushing water. And indeed, life itself finds home in those newborn scars, around the cracks where lava still oozes hydrothermal vents, erupt in black clouds of minerals nourishing entire ecosystems of creatures that never see sunlight, tube worms, ghostly, shrimp-blind crabs. They thrive on the chemistry of the deep, on hydrogen, sulfide, iron, and heat. For them, the basaltic crust is both bedrock and banquet table. What for us seems lifeless stone is in the abyss a foundation for creation. Basalt, the substance of this oceanic armour, is simple yet ancient in recipe. It is born from the partial melting of mantle rock, rich in iron and magnesium, low in silica. That chemistry makes it fluid, allowing it to flow easily before cooling. It is denser than the granitic crust of continents, so dense that when the two meet, the oceanic plate always sinks beneath the continental one, returning to the mantle from which it came. Thus the armour is temporary, forever forged and consumed. No part of it survives beyond a few 100 million years. The ocean's skin is young even when its waters are old. Seen from above through the eyes of sonar, the seafloor looks like a frozen battlefield of motion ridges, where new crust forms trenches, where old crust is swallowed, volcanoes rising like sentinels along the faults. The basaltic shell may seem impenetrable, but it is riddled with fractures continually cracking as the plates move apart. Through those fissures, seawater seeps down into the hot rock, reacts with it, and returns to the surface laden with metals and gases. In this way, the crust breathes it, exchanges, circulates, participates in the Earth's metabolism. Every pillow, every layer of basalt is part of that grand breathing system. The dark armour of the ocean is not static, it is both skin and lung boundary in exchange. Its surface defends the mantle from the sea, yet its cracks allow the two realms to converse, trading heat and chemistry. Without it, the planet's thermal and mineral cycles would falter. The oceanic crust is Earth's quiet mediator, standing between the deep fire and the cold abyss. And though we rarely see it, this armour covers most of our world. Mountains, forests, deserts, all of them together are small islands upon a sea of basalt. When you look at a map, the continents seem to dominate, but in truth they are the exceptions. The true face of the planet lies beneath the waves, dark, dense, ever-renewing. If we could lift the oceans away, the sight would be otherworldly, a landscape of black glass and twisted sculpture, ridges glowing faintly from the warmth of the mantle below. You would see the artistry of molten rock in every curve, every frozen wave, every pillow-shaped fragment of stone. This is the Earth's armour, born in darkness, quenched by water, destined to return to fire. Even in the coldest depths, creation continues. The planet does not sleep, it only whispers more quietly beneath the sea. There are moments when the Earth creates not stone but glass, moments so swift and violent that the ordinary rules of crystallization collapse. Lava meets cold air or water, freezes before its atoms can organize and solidifies into a smooth, dark mirror. This is obsidian volcanic glass, born in a heartbeat, a fusion of fire and stillness. It is one of nature's purest paradoxes, at once fragile and eternal, delicate enough to shatter, yet sharp enough to outlast civilizations. Obsidian forms when molten rock rich in silica cools too quickly for minerals to crystallize. Normally, as magma cools, its atoms arrange themselves into orderly lattices, quartz, feldspar mica. But when the cooling is instantaneous, when the lava spills into a lake or erupts into cold mountain air, the atoms freeze in place, locked in disarray. The result is a solid without structure, smooth as water, made permanent. It reflects light like black ice, and fractures with a silky curve known as a conchoidal, break a geometry so precise that ancient toolmakers across the world prized it above all others. To hold obsidian is to hold the memory of fire that refused to slow down. It is glass forged in chaos, born from the narrow margin between eruption and stillness. In Iceland, obsidian lies scattered among cooling lava fields like shards of night. In Mexico and the American Southwest, entire mountains glitter with its remnants of explosive eruptions where rheolitic magma turned to glass mid-breath. On Easter Island, the islanders carved their sacred statue's eyes from it, believing that the black gleam gave life. In ancient Anatolia, obsidian blades travelled in trade long before metal was known. To Neolithic hands, it was the first high technology. A freshly fractured edge of obsidian can be sharper than surgical steel. Its atomic smoothness produces cutting edges only a few molecules thick. Archaeologists have found obsidian scalpels still capable of slicing with surgical precision after thousands of years. Yet that same perfection is its weakness. Because it lacks the crystalline structure that gives stone its toughness, a single impact can shatter it like ice. Fragility and strength bound together in one material, the duality of creation itself. Culturally, obsidian has always hovered between the earthly and the mystical. The Aztecs called it Itzli, the blood of the earth. They fashioned mirrors from it, black reflective portals through which priests and shamans claimed to see the spirit world. In ancient Mesoamerica, the god Tezcatlipoca carried such a mirror on his chest, its surface reflecting not the face of the beholder but their soul. Across the world, from Armenia to Japan, obsidian held a similar fascination. Its smooth darkness seemed alive, a captured shadow, a material that remembered both fire and night. Even in modern science, obsidian remains a wonder of extremes. Under the microscope, it reveals almost no structure, just a random arrangement of silicon and oxygen atoms frozen in disorder. Yet from this disorder emerges beauty, subtle flow lines preserved from its molten motion, microscopic bubbles like trapped breath, delicate sheen that can shift from silver to green depending on the light. When lightning strikes sandy beaches, it sometimes creates fulgurites, glassy tubes of fused quartz, a cousin of obsidian born not from magma but from a flash of energy. Both are messages written in glass, one from the sky, one from the deep earth. To geologists, obsidian is a clue about the speed of cooling, the chemistry of magma, and the violence of eruption. But to the imagination, it is something deeper, proof that chaos can yield clarity. It reminds us that perfection sometimes arises from failure. When the crystal lattice cannot form, when order breaks down, beauty appears. In that frozen disorder lies symmetry of another kind, one sculpted not by patience, but by catastrophe. And like all volcanic creations, obsidian is transient. Over time, water seeps into its glassy surface, breaking the atomic bonds and slowly turning it back into stone through a process called devitrification. The glossy surface dulls, fine crystals bloom within. Even glass cannot resist the long persuasion of time. Yet before it fades, it remains a perfect paradox, a moment of molten fire captured mid-breath, neither liquid nor solid, fragile yet enduring. When ancient peoples shaped it into arrowheads or mirrors, they were not merely crafting tools, they were capturing a heartbeat of the earth. Every shard of obsidian is a frozen instant of eruption, a record of energy transformed into calm. In its darkness, you can see reflections of stars, your own eyes, the faint shimmer of the volcano's vanished flame. It is easy to forget in our world of steel and silicon that the first true glassmaker was the planet itself. Long before humans learned to melt sand or forge metal, the Earth had already perfected the art of light trapped in darkness. Obsidian is the planet's reminder that creation and destruction are one motion, the flash where heat becomes memory, where fire learns to hold still. If you hold a piece of volcanic rock to the light, you might see tiny perfect hollows glimmering inside, each one no bigger than a grain of sand, each one a bubble of something invisible. Those small voids are not empty. They are filled with time. They contain the whispers of vanished atmospheres, the breath of worlds the Earth once was. When molten rock rises from the mantle, it carries with it gases dissolved under immense pressure, carbon dioxide, water vapor, sulfur dioxide, and traces of argon, neon, and helium. Deep underground, these gases are compressed into the melt like air in a sealed bottle. But as the magma ascends and pressure drops, the gases expand, forming bubbles that grow and rise, just as they do in boiling water. When the lava erupts and cools, the rock solidifies around those bubbles, trapping them forever. Each one becomes a tiny time capsule, preserving the air of that moment, the chemistry, the pressure, the volatile soul of the planet. These trapped pockets are called vesicles, and the rocks that contain them, basalts, pumice, scoria, are like archives of the Earth's exhalations. To geologists, they are treasure. Within them lie records of ancient volcanic gases, of how the early atmosphere gained and lost its elements, of how oceans and climates were born and transformed. When these vesicles are studied under microscopes or pierced in vacuum chambers, they release gases that have been sealed since the moment the lava froze. Each sample is a frozen conversation between Earth and sky. In the oldest basalts on Earth, scientists have found gases that predate life itself, traces of helium and neon, with isotopic fingerprints inherited from the planet's formation. These are whispers from the deep mantle reservoirs of the primordial air that first wrapped around the young Earth billions of years ago. They tell us that some parts of the interior have remained isolated since the beginning, untouched by the cycling of crust and ocean. You can think of these bubbles as a kind of planetary memory, storing snapshots of evolving atmospheres through deep time. In rocks from ancient flood basalts like the Deccan and Siberian traps, the vesicles reveal how massive eruptions pumped carbon dioxide and sulfur into the sky, driving climate swings and extinctions. In younger lavas, the gases show how volcanic activity still renews the air, releasing carbon, water, and nitrogen that balance the atmosphere and sustain life. The bubbles are tiny, but together they chronicle the Earth's breathing, its long rhythm of exhalation and renewal. Some bubbles come not from eruptions, but from glaciers. Ice cores drilled in Antarctica and Greenland contain pockets of ancient air that complement the story told by stone. Those bubbles, thousands to hundreds of thousands of years old record shifts in carbon dioxide and methane, capturing the heartbeat of the ice ages. In rock and ice alike, air is the historian's soft, invisible, but enduring. On a planetary scale, even the tiniest trapped gas can shift our understanding of time. When a basalt pillow from the seafloor yields argon isotopes from its vesicles, scientists can date its solidification with extraordinary precision. The air inside becomes a clock. When pumice from an eruption holds sulfur dioxide residues, it tells of atmospheric cooling that may have altered global weather for years. The gases in rocks are not relics, they are data, and their quiet testimony connects the geology beneath us to the sky above. Sometimes these bubbles tell stories that feel almost human. On the slopes of Mount Etna, recent lavas contain traces of carbon dioxide that match the signature of industrial pollution, evidence that our species too now contributes to the chemistry of the planet's breath. Our air, like the ancient ones, will one day be sealed into rock, becoming part of the next geological archive. The planet will remember us in bubbles. There is poetry in that idea. Every gas pocket, every vesicle, every glassy bead of lava is a memory of pressure, of heat, of release. It is the fossilized form of a sigh, the planet's inhalation caught mid-breath. In those hollow spaces, the Earth keeps record of its changing sky, the birth of oxygen, the waning of carbon dioxide, the slow cooling of the world. When scientists slice open these stones and free the gases within, it is as if they are opening letters from deep time. Each whisper of helium, each puff of carbon dioxide, is a word in a language the planet has been speaking since it first cooled. And so, scattered across mountains, ocean ridges and deserts, the Earth's breath endures in bubbles no bigger than a pinhead. They remind us that air, though fleeting, can last longer than stone when sealed by fire. If you could listen closely to one of these bubbles as it bursts open in a lab, you might almost hear it. A faint exhale from an age when continents were unborn, oceans young and the sky still learning what colour to be. The planet keeps its memories in the smallest of places, and sometimes the silence inside a stone is the sound of ancient air. Beneath the waves lies a world more mountainous than any on land. If the oceans were drained, you would see a planet unrecognizable, vast ranges stretching from horizon to horizon, volcanic peaks taller than Everest valleys, deeper than any canyon cliffs plunging into darkness where sunlight has never touched. This is Earth's hidden topography, a landscape greater in scale and mystery than all the continents combined, the mid-ocean ridges, the mountains under the sea. These ridges are the beating heart of plate tectonics, the seams where the planet continually renews itself. They form a single continuous chain of volcanoes encircling the globe for more than 65,000 kilometers, the longest mountain range on Earth. From the Arctic Ocean to the South Pacific, from the Atlantic spine to the Indian Ocean's triple junction, they rise from the abyss like sleeping giants, their crests shrouded in eternal night. At the mid-ocean ridges, the planet is literally tearing open. Molten rock from the mantle wells upward through fractures, cools and hardens into new crust. As more magma emerges, it pushes the old crust aside, widening the oceans. What we think of as still sea floor is in truth a conveyor belt of creation moving away from these ridges at a rate of centimeters per year. The Atlantic, for instance, is widening even now, while the Pacific's older crust is being swallowed in the trenches that fringe its rim. Seen through sonar mapping, the ridges appear like great scars, zigzagging lines of peaks and valleys. Their central rift valleys can be several kilometers deep and dozens wide, where the crust is stretched thin enough for magma to rise. Along these crests, black smokers and hydrothermal vents spout mineral-rich water heated to hundreds of degrees, feeding entire ecosystems that depend not on sunlight but on chemistry. Here, bacteria convert sulfur and iron into energy, forming the base of a food web that supports tube worms, clams, crabs, and strange white fish with mirror-like eyes. In this darkness, life glows faintly. Bioluminescent creatures drift like lanterns, their light echoing the planet's hidden fires below. The ridges pulse with heat, yet their peaks lie shrouded in pressure so immense that water becomes something denser than we imagine a substance that can crush steel but cradle life. These submarine mountains are alive in their own slow rhythm, magma rising, cooling, cracking, venting, rebuilding. The scale is staggering. The ridge system beneath the Pacific can rise 3 kilometers above the abyssal plains, rivaling the height of the Himalayas when measured from base to summit. In the Atlantic, the Mid-Atlantic Ridge splits Iceland in two, its rift valley running like a scar across the island's center, a rare place where we can walk upon what elsewhere lies hidden. In the Indian Ocean, 3 ridges meet at a point called the Rodriguez Triple Junction, where the planet's plates diverge like the petals of a slow, fiery flower. Everywhere along these ridges, the crust is youngest, barely a few million years old. As one moves away from them, the seafloor ages, thickens, and cools, sinking deeper into the mantle. The ridges, therefore, are not just mountains, they are the frontiers of time. Each ridge crest marks the present moment of creation, while the abyssal plains beyond are the past moving outward like pages turning in a book that never ends. It is humbling to realize that we know the surface of the Moon and Mars in greater detail than the terrain beneath our own oceans. Only in the last century have we begun to map these hidden mountains using sonar echoes to paint relief where eyes cannot see. Before that, the seafloor was myth, a blank void on maps labelled simply unknown. Now we know it is anything but. The seafloor is sculpted with volcanoes, faults, valleys and plateaus. Its geography is dynamic, restless, alive. Each ridge is a workshop of planetary invention. The basaltic crust that forms there spreads outward, cools fractures, and becomes the foundation for coral reefs, continental margins, and the islands that rise from the sea. Even the continents owe their shape in part to the slow rhythm of these underwater builders. Over millions of years, as ridges shift and change, they guide the circulation of the oceans, influencing climate currents and the migration of life. And yet, for all their importance, the mid-ocean ridges remain mostly unseen. No sunlight ever reaches their summits. The peaks of these mountains dwell in perpetual night, bathed only in the faint blue of submersible lights or the glow of vent organisms. They are the silent continents of the deep places where creation continues unnoticed, where the earth still speaks the language of fire and water. If you could descend there beyond the reach of sound and storm, you would see a world unlike any other. You would glide over ridgelines that stretch farther than the Andes over vents, breathing clouds of silver minerals over plains littered with pillow lavas and living smoke. The pressure would be crushing the water near boiling, yet life would shimmer all around, a reminder that even in the darkest places the planet's heart beats steadily. The mountains under the sea are Earth's secret face, immense, unseen, and ceaselessly alive. They are where the world renews itself one eruption at a time, shaping the future in darkness, while we dream above the waves. At the edge of the Pacific, east of the Philippines, the ocean suddenly falls away. Its surface, calm as a mirror, hides a wound in the planet's crust, the Mariana Trench, a chasm nearly 11 kilometers deep. If you dropped Mount Everest into it, the summit would still lie submerged under 2 kilometers of water. It is the lowest known point on Earth, a place where the seafloor bends, cracks, and disappears into the planet's interior. This is the deep heart of the world, the frontier between surface and mantle, between light and the unseen. The trench is formed by subduction, the process where one tectonic plate dives beneath another. Here, the Pacific plate, dense, cold, and ancient, slides under the smaller Mariana plate at a rate of a few centimeters per year. As it descends, it drags with it a record of the ocean floor sediments, fossils, crust, and water. The descent continues for hundreds of kilometers until the rock melts, feeding volcanoes far inland. This invisible conveyor belt is part of Earth's recycling system, the same cycle that renews continents and shapes climates. But at the point of descent, where the crust first begins to sink, the ocean becomes something else entirely. The Mariana Trench is not just a single crack, but a complex system of ridges, arcs, and valleys stretching for over 2,500 kilometers. Its deepest point, the Challenger Deep, is a small basin, only a few kilometers wide. The pressure there exceeds 1,000 atmospheres, more than 8 tons per square inch. It would crush a human body, flatten an instant collapse steel, and squeeze air into liquid. Yet even here, where no sunlight has ever reached, life persists. In 1960, when Jacques Picard and Don Walsh descended in the Trieste, they saw something move, a flatfish-like creature stirring the sediment at nearly 11,000 meters. Later expeditions with robotic submersibles confirmed it, the trench teems with strange forms of life. Microbes thrive in sediments that smell faintly of ammonia and iron. Amphipods, tiny shrimp-like crustaceans, swim in slow spirals, their bodies adapted to pressures that would liquefy ours. Even bacteria live inside the rocks, feeding on hydrogen and methane that leak from the subducting crust. Life here does not survive despite the darkness it depends on it. The deep ocean is an ecosystem sustained by chemistry rather than light. At the surface, life feeds on sunlight. In the abyss, it feeds on energy from the Earth itself. As the descending plate carries seawater deep into the mantle, the water reacts with the rock, forming hydrogen and other molecules that become food for microbes. These microorganisms in turn form the foundation of entire food webs that extend upward through the trench. In this eternal night, life glows faintly from within, a slow, chemical luminescence powered by geologic energy. To imagine this world, think of the planet's surface as the skin, and the trench as a vein leading into its body. Down there, the walls are steep and jagged, layered with basalt and sediment, crushed into metamorphic stone. Currents move sluggishly, carrying particles that have drifted for centuries. Every so often, a tremor shakes the floor, an echo of the subduction zone's immense strain. The crust bends, fractures, releases its grip, and the Earth quakes. These earthquakes, though invisible to us, are the pulse of subduction and the steady heartbeat of the deep. The descent of the oceanic plate has another consequence. It draws carbon, water, and organic material down into the Earth's interior. Over millions of years, these materials are recycled, returning to the surface through volcanic eruptions. The carbon dioxide released from volcanoes is in part the breath of ancient seas. Even the rain that falls on continents may contain atoms that once lay trapped in a trench. Nothing is lost. Everything circulates. The Mariana Trench is not a grave, it is a doorway in that endless cycle. Still, the environment there feels alien. Temperatures near freezing, total darkness, pressure beyond comprehension, and yet in this place life may hold secrets to endurance unknown elsewhere. The enzymes and cell membranes of deep-sea microbes withstand forces that would rupture any known organism. Their biochemistry has become a model for exploring not only Earth's extremes but potential life on other worlds, Europa Enceladus, or the icy moons whose oceans may resemble our own abyss. The deeper one goes, the more paradoxical the landscape becomes. At 10,000 meters, the crushing weight of the ocean paradoxically prevents boiling even near vents, where heat seeps up from below. Water can remain liquid well above 100 degrees, forming a superheated broth, rich in dissolved metals and gases. Out of that cauldron, mineral chimneys rise encrusted with crystals, feeding colonies of microorganisms that shimmer like dust caught in faint light. The trench is both furnace and freezer laboratory and tomb. If you could stand there, though, nobody could, you would see the ocean above as a ceiling of ink. Particles of detritus marine snow would fall past you like slow-motion rainflakes of organic matter, drifting down from the surface world. Each one might take months to reach the bottom, nourishing life that never knew the sun. Occasionally, the faint glow of bioluminescent creatures would pass by, momentary stars in a private universe. The Mariana Trench is proof that life's persistence is not bound to comfort. It endures in silence, in pressure, in dark. And as the Pacific Plate continues to dive beneath its neighbour, the process that created this trench continues inch by inch, century by century. The deepest place on Earth is not a relic of the past, but a living part of the planet's engine. It is where creation and destruction are the same act. The next time you look at the ocean, remember what lies beneath a world of mountains turned upside-down valleys where stone bends and melts and life thriving where it should not. The deep heart of the Earth beats quietly far below us in darkness that has never seen the sun, and it is still alive. The Earth is never silent. Even when the wind stops, even when the night is still and the sea is calm, the ground beneath us murmurs. Beneath the hum of cities and forests, an older vibration continues, faint tremors, imperceptible shifts, the slow settling of a living crust. The planet speaks in whispers of pressure and release in the quiet dialogue between stone and time. Most of these movements are too small for human senses. They are called micro-earthquakes, tremors, so gentle they register only on instruments. Every minute, thousands ripple through the crust somewhere in the world, tiny adjustments. A long fault slips as plates inch past one another, sighs of expansion and contraction, as magma cools or groundwater drains. To seismologists, these signals are the background heartbeat of a restless planet. To the Earth itself, they are simply breathing. Each fault line, each buried fracture in the crust is like a string on an immense instrument. When stress builds along it, the rock bends and holds until it suddenly releases, vibrating through the crust. Large quakes are the loud chords, the ones we feel, the ones that break cities. But far more common are the inaudible notes, microquakes, that hum, constantly dissipating tension before catastrophe. They are the Earth's way of maintaining balance, a million small corrections instead of one great rupture. Modern instruments can now detect these faint murmurs with exquisite precision. Arrays of seismometers buried in bedrock record vibrations measured in nanometers less than the width of a human hair. Under their electronic ears, the Earth's surface is alive with motion. They reveal patterns invisible before slow slips along faults that take days instead of seconds, pulses that migrate down rift zones like subterranean waves, deep tremors beneath volcanoes that hint at rising magma. The ground we stand on is not rigid but elastic, quivering like a drum stretched over molten depths. Some of the most haunting of these sounds come from silent faults, where plates move smoothly rather than in violent jerks. The San Andreas Fault in California, for instance, is mostly quiet. Most of its motion occurs through slow, steady creep a few millimeters a year, so gentle that it produces little shaking. But deep beneath at the locked segment, stress accumulates in silence, building toward the inevitable release that will one day speak loudly again. Between those moments of chaos, the planet whispers reassurance, I'm still adjusting. The ocean floor too hums with subtle motion. Hydrophones underwater, microphones record a ceaseless chorus of clicks, rumbles and groans, the crack of basalt cooling at mid-ocean ridges, the long sigh of seafloor spreading the distant echoes of icebergs grounding on continental shelves. Even waves slamming against cliffs send vibrations through the crust that circle the globe. Geophysicists call this continuous background the Earth's hum, a low-frequency resonance that never ceases, a sound too deep for our ears, but always present. Volcanoes have their own language of whispers. Before an eruption, they often emit harmonic tremors, repetitive musical vibrations produced by magma pulsing through conduits. The tones can resemble organ notes, sometimes rising in pitch as pressure builds. Scientists monitor these frequencies like cardiologists reading a heartbeat. When the tone steadies, the volcano sleeps. When it quickens, the mountain begins to stir. Even the solid continents breathe. In winter, when snow piles upon mountain ranges, their weight compresses the crust by millimeters. When the snow melts, the crust rebounds upward. The same happens with tides. The pull of the moon flexes, the crust rhythmically raising and lowering it twice a day by centimeters. Sensitive instruments record these oscillations like slow waves passing through stone. To us they are imperceptible. To the Earth they are lullabies. Listening to the planet's whispers has become a kind of deep time symphony. Networks of seismographs around the world now share data in real time, allowing scientists to hear the subtlest stirrings anywhere on the globe. Sometimes they detect what are called slow earthquakes events that release energy gradually over weeks or months rather than seconds. They do not shake buildings, but they shift entire regions by centimeters. Japan, New Zealand and Cascadia all experience these hidden quakes, ghostly preludes to larger ones that may follow. It is humbling to know that even when we sleep, the ground is in motion, always flexing, always adjusting to its internal geometry. A boulder settling in a mountain stream, a glacier grinding over bedrock, the cooling of magma beneath an island, all send small ripples through the crust. If you could amplify those signals, the world would sound like a great slow orchestra. Deep percussion from subduction zones, tremolo from rift valleys, faint bells from volcanic arcs. The music never ends, it only shifts in tempo. In the end, these whispers are the proof of life beneath our feet. A dead planet would be silent, but Earth hums and sighs, cracking, healing, renewing itself constantly. It may roar in earthquakes or speak softly through micro-tremors, but it always communicates. To live upon this planet is to stand upon a living instrument feeling only the quietest notes of a song that began long before us and will continue long after. If you could lie down on the bare ground and listen, not with your ears but with your imagination, you might sense that hum, the faint vibration of stone beneath stone, the low pulse of magma moving far below the sigh of a planet adjusting itself endlessly. These are the Earth's whispers, its language of patience, of pressure, of balance, the sound of a world alive. Sometimes the Earth moves not as a whisper, but as a command. In a few terrible seconds, continents shift, mountains lurch, and rivers, those patient sculptors of valleys, forget which way to flow. The laws of direction honed over millennia reverse themselves. The Mississippi has done it. The Amazon too. For a brief astonishing moment, the planet's geometry changes so violently that water obeys a new gravity. Such events begin deep beneath our feet, where strain has been building invisibly for centuries. Tectonic plates do not glide smoothly, they grind and stick. Along locked faults, stress accumulates until the rock suddenly ruptures, releasing energy equivalent to thousands of nuclear bombs. The ground ripples like water in a pond. Seismic waves race outward through the crust, bending everything they touch. When those waves pass under rivers, they can tilt entire basins for minutes enough to make the impossible happen. One of the most dramatic examples occurred along the New Madrid Fault in the winter of 1811 to 1812 in what is now the central United States. Over a period of months, a series of massive earthquakes struck the Mississippi Valley, each shaking the frontier settlements from St. Louis to Memphis. Eyewitnesses reported the river itself rising up in walls of frothing brown water. In places it appeared to flow north instead of south, rushing backward against its own current. Sand erupted from the ground in fountains. Entire islands vanished. The riverbanks collapsed, forests sank, and newly formed lakes appeared overnight. What those witnesses saw was not magic, but physics on a planetary scale. As the quake's seismic waves passed beneath the region, they caused the crust to warp, raising the land south of the river, while dropping the land to the north. For a few minutes, the gradient that had guided the Mississippi for thousands of years reversed. Water obeyed gravity's new direction, surging backward until the land relaxed again. When the motion subsided, the river returned to its course, leaving behind whirlpools, sunken forests, and astonished survivors. Something similar happened in other great earthquakes. During the 2004 Sumatra-Andaman quake, the seafloor rose by several meters, displacing billions of tons of water and triggering a tsunami that circled the globe. In some rivers of Thailand and Indonesia, the flow reversed temporarily as the ground flexed. During the 2011 Tohoku earthquake in Japan, sensors recorded rivers flowing backward for minutes as the land near the coast abruptly subsided, pulling seawater inland. The world's solid crust, which seems eternal, revealed itself as supple as cloth. The reversal of a river's flow may last only minutes, but it is a reminder that equilibrium is an illusion. The landscapes we trust, the courses of rivers, the tilt of valleys, even the level of the sea are contingent on a balance that can be broken in a single heartbeat. The physics of a great quake is the physics of release energy long restrained by friction suddenly freed. The result is motion that ripples through everything built upon the crust mountain cities and the soft obedient water that follows gravity wherever it points. During such upheavals, even the air records the shock. In 1811, people across the eastern United States reported strange rumblings like distant thunder. Church bells rang in Boston. The Mississippi's reversal was only one visible symptom of a planet momentarily reconfiguring itself. Lakes appeared where prairies had been. Faults tore open, ground rose and sank by meters. Yet within weeks the land settled into a new equilibrium, as if nothing had happened. The river resumed its southward march to the Gulf, carrying with it trees, debris, and the memory of its brief rebellion. Modern instruments now capture what the old witnesses could only describe in awe. GPS stations reveal that major earthquakes can permanently shift entire regions by meters. The 2011 quake in Japan moved parts of Honshu 8 feet eastward. Chile's 2010 event shortened the day by a microsecond. These are not poetic exaggerations, they are measurable changes in the planet's rotation, subtle adjustments in the balance of mass. The Earth is elastic, but not infinitely so. When it shifts, everything above responds. Rivers with their ancient patience show us this most vividly. They have no will, only obedience. When the ground beneath them tilts, they follow instantly, reversing centuries of erosion and habit. It is as if time itself falters for a moment, mountains breathe, the land flexes, and the waters forget the way home. For those who witness such moments, the sensation is disorienting beyond words. Imagine standing on the bank of a river you've known all your life, and seeing it surge in the wrong direction, trees, boats, entire sections of shore swept upstream. It is a sight that erases certainty, that reveals how fragile our sense of up and down truly is. And yet in the aftermath order returns. The same gravity that was briefly rewritten reasserts itself. The planet, having vented its tension, settles back into stillness. The river resumes its song as if nothing had changed, though somewhere in its depths, a faint memory remains a whisper of that moment when the Earth tilted and the flow of time ran backward. When we speak of natural disasters, we often imagine destruction, but there is also something sublime in these transient inversions. They remind us that the ground we trust is alive, responsive, capable of reshaping its own geometry in the blink of an eye. The Earth is not a stage, it is a performer improvising endlessly, sometimes so quietly that we forget it moves at all, and sometimes so powerfully that even rivers lose their way. The day the rivers ran backward was not a mistake of nature. It was the planet reminding itself of its own flexibility, its ability to bend and recover, to unleash and then heal. It was awe captured in motion chaos giving way again to calm. Not every earthquake announces itself with violence. Some unfold in silence, their motion so gradual that not a single glass trembles, not a leaf stirs. Beneath the ground, rock moves anyway, creeping, inching, adjusting. This is the other face of tectonic power, slow, slip, the invisible easing of strain that allows the planet to balance destruction with calm. The Earth, it turns out, can exhale quietly too. In most places along the world's faults, rocks lock together under immense pressure. For years, decades, even centuries, the two sides strain against each other until they finally break free, releasing energy as a quake. But in certain zones, especially near the brittle ductile boundary deep underground, the rock behaves differently. Instead of locking and snapping, it flows. The result is a fault that creeps, a steady, almost imperceptible movement that relieves stress without shaking the surface. These creeping faults are like pressure valves in the planet's architecture. They slide continuously a few millimeters or centimeters per year, allowing the crust to rearrange itself quietly, while neighboring regions hold their breath. California's Hayward Fault, for example, moves in this silent way, inching northward under sidewalks and fences in Oakland and Berkeley. Over decades, curbs, misaligned roads bend and houses twist slightly, not from quakes, but from the Earth's slow insistence on motion. To geologists, this behavior is both reassuring and mysterious. On one hand, creeping faults release strain, gradually preventing the buildup that causes catastrophic quakes. On the other, they can sometimes transfer stress to locked sections nearby, priming them for future rupture. It is a delicate balance, a choreography of motion and stillness, where one segment's calm can be another's prelude. The planet's surface, though it seems steady, is a system of negotiations. The discovery of slow slip came not through sound or sight, but through measurement. In the 1990s, GPS sensors began revealing movements no one had expected, regions that shifted not in seconds, but over weeks or months. The ground would creep several centimeters, pause and then settle back without a single tremor felt at the surface. These slow earthquakes, as they came to be known, release the same amount of energy as large conventional quakes, but stretched over time so that the energy disperses gently. They are the planet's way of sighing instead of screaming. In places like Cascadia, the vast subduction zone off the Pacific Northwest, slow slip events occur every year or two. For weeks, the coastline inches westward as the deep part of the fault glides smoothly. Then just as quietly it stops. Instruments record this as a wave of motion moving hundreds of kilometers along the fault like a tide beneath the continent. Locals never feel it, yet it shifts the entire Pacific Northwest, closer to the next great earthquake by a fraction of a millimeter. The land breathes in, then out. Similar phenomena have been recorded in Japan, New Zealand, Mexico, and Alaska. Each slow slip is accompanied by faint low-frequency tremors, a sound too deep for human hearing, like a distant growl of the planet's machinery. Scientists now map these hidden pulses to understand how energy travels through the crust. What emerges is not a picture of sudden violence, but one of continual adjustment, a world constantly fine-tuning its own stresses, avoiding catastrophe through ceaseless motion. There's a strange comfort in this revelation. The Earth is not a clockwork wound tight until it breaks. It is a living system that knows how to release to balance, to move gracefully when it can. For every great quake that tears a city apart, there are 1,000 slow ones that pass unnoticed, quietly preventing worse. The planet's stillness, we now know, is not truly still. It is stability maintained by motion too slow to see. Even mountains, those symbols of permanence, are participants in this silent dance. Along their buried roots, faults creep and slip, reshaping the land grain by grain. What looks solid to us is only a temporary truce between forces of uplift and erosion, compression and expansion. The ground beneath your feet is always negotiating its position in the world. To walk upon such a planet is to live on a surface constantly correcting itself. The creeping faults are not errors, they are the mechanisms of resilience. They absorb pressure, distribute tension, and remind us that gentleness too is a form of strength. The same earth that can shatter mountains can also adjust with patience, healing itself through tiny movements. If you could watch the crust in time-lapse, centuries passing in seconds, you'd see the ground undulating subtly, like the surface of a sleeping animal. Faults sliding strata, bending pressure, rising and falling in endless exchange. The Earth is never at rest, but it is rarely in chaos. Between its roars are long-measured breaths. In a sense, we owe our existence to those breaths. Without the planet's ability to release tension gradually, the crust might fracture beyond repair. Oceans, continents, even the atmosphere all depend on this delicate equilibrium between sudden and slow, between earthquake and exhale. The creeping faults are Earth's lesson in balance, that even immense power can choose restraint, that not all strength must announce itself with noise. So the next time the ground feels still, remember what that stillness means. It is not silence, but harmony, the quiet music of rock slipping past rock of tension, dissolving in patience. The planet is speaking always in movements too slow for us to feel. Its whispers are the sound of peace being made beneath our feet. Beneath every mountain, beneath every ocean, beneath even the deepest trench, there lies a world no human has ever seen. It is hotter than the surface of the sun, denser than any metal we can forge, and under pressures that crush atoms into new forms. This is the core, the Earth's iron heart, hidden more than 6,000 kilometers below your feet. Though it is sealed away from sight, its motion and heat sustain everything above it. Without that secret engine, there would be no magnetic field, no protection from solar wind, and perhaps no life. The surface world owes its calm to the raging furnace below. The journey inward begins with a change of state. Beneath the thin crust and the viscous mantle lies a boundary known as the Gutenberg discontinuity, where solid rock gives way to molten metal. Here, at a depth of about 2,900 kilometers, the outer core begins a vast ocean of liquid iron and nickel swirling at temperatures between 4,000 and 6,000 degrees. The pressure is so immense that iron, which would vaporize in any furnace on the surface, remains fluid. This metallic sea extends for another 200 kilometers downward, circling the planet like a restless heart conducting electricity and heat with astonishing efficiency. At its center lies the inner core's solid sphere of crystallized iron, roughly the size of the moon. It is the most inaccessible place imaginable. Temperatures approach 6,500 Gauss. But the pressure more than 3.5 million times that at the surface forces atoms into tight metallic lattices. The inner core is slowly growing as the planet cools, solidifying grain by grain. Each atom that freezes releases latent heat, driving convection in the liquid outer core above. That motion, metallic, turbulent, eternal, is what keeps the planet alive. Because liquid iron is an excellent conductor, its movement generates electric currents. These currents in turn produce magnetic fields, and as the molten metal spirals and heaves in complex self-sustaining patterns, Those magnetic fields weave together into a planet-sized dynamo, a geodynamo. It is a paradox of nature chaos, giving rise to order turbulence, creating a stable magnetic shield that envelops the entire Earth. This invisible field extends far into space, forming the magnetosphere, a protective cocoon that deflects charged particles streaming from the sun. Without it, the solar wind would strip away our atmosphere just as it did to Mars. The auroras, the dancing lights near the poles, are the visible fingerprints of that magnetic shield, glowing where the solar particles graze our upper atmosphere. They are in essence the northern and southern reflections of the planet's inner fire. We can't see the core directly, but we can listen to it. Seismic waves from earthquakes travel through the planet and change speed when they cross different layers. By studying how those waves bend and reflect, geophysicists have mapped the core's structure with astonishing precision. They can tell that the outer core is liquid because certain earthquake waves' shear waves cannot travel through it. They can tell that the inner core is solid because others pass through and refract as if glancing off crystal. In this way, the Earth's heart has been seen not with eyes but with echoes. It is not entirely still. The inner core appears to rotate slightly faster than the rest of the planet, a phenomenon called superrotation, completing an extra spin every few centuries. Its surface may be lopsided, one hemisphere crystallizing faster than the other. Even the direction of solidification shifts over time, subtly altering the strength and geometry of the magnetic field above. What we experience as the slow drift of magnetic north, or the occasional reversal of the poles, is the surface reflection of molten currents through 1,000 kilometers deep. Over geological time, the geodynamo has flickered but never failed. Every few 100,000 years, the field weakens, fragments, and reverses. North becomes south, and compasses would point the other way if any existed to feel it. Rocks remember these reversals in their magnetic minerals, tiny compass needles frozen in ancient lava. Through them, we know that the core's heartbeat has pulsed steadily for billions of years. Even when its rhythm changes, its energy never ceases. What powers this iron heart? Some of its heat comes from the planet's birth. The leftover energy of accretion when countless meteorites fused into a single sphere. Some comes from radioactive decay of heavy elements like uranium and thorium, which release heat as they disintegrate. And some comes from the crystallization of the inner core itself, a process as elegant as it is relentless. Together, these sources keep the outer core molten and convecting, driving the magnetic field that shields our fragile world. It is strange to think that our survival depends on something we can never touch. The outer core lies deeper than any drill will ever reach, the inner core forever beyond our machines. Yet its influence surrounds us every day. Every compass needle twitching toward north, every aurora flickering green over polar skies, every protection our atmosphere affords, all are signs that the heart still beats. In the far future, billions of years from now, the Earth will cool. The outer core will freeze solid, the geodynamo will stop, and the magnetic field will fade. The solar wind will begin stripping away the air, and the planet will slowly lose its shield. But that time is far beyond us. For now, the iron heart still turns, still burns, still hums beneath our feet. If you could somehow stand there on the smooth metallic surface of the inner core, you would feel no wind, no sound, no up or down. The pressure would crush steel, and yet the material around you would flow like honey. Above, molten iron currents would twist and churn, each eddy shaping the invisible field that guides migrating birds, deflects cosmic rays, and anchors human compasses. The center of the world is not stillness, it is motion, eternal and unseen. The Earth's iron heart beats in silence, but its pulse surrounds us. Every sunrise protected from the sun's fury, every whisper of a compass needle, every soft shimmer of the aurora, is proof deep below the planet's heart is still alive, and it has been beating for 4.5 billion years. When we look at the blue horizon and call ours a water planet, it feels like a complete truth. But the seas that cover Earth's surface, the Pacific, the Atlantic, the Indian, the Arctic, the Southern, may only be half the story. There is another ocean, older, darker, and deeper than any trench one that no light has ever touched. It lies not above the crust, but within it, locked inside the crystal structure of rocks, hundreds of kilometers below. This is the hidden ocean, a reservoir vast enough perhaps to equal or even exceed all the water we see. To understand it, we must travel downward into the mantle, where pressure and temperature transform ordinary minerals into strange new forms. Around 400 to 700 kilometers deep lies a region known as the transition zone, sandwiched between the upper and lower mantle. Here, minerals such as olivine, so common in Earth's upper layers, rearrange themselves under crushing force. Their atoms shift and new structures emerge, waddsleite and ringwoodite exotic crystals that can trap water molecules not as liquid but as hydroxyl groups, tiny fragments of H2O woven into the mineral lattice itself. Each grain of these minerals may contain only a trace of water, less than 1% by weight, but the mantle is unimaginably vast. Multiply those traces by the volume of the entire transition zone, and the numbers stagger belief. If released to the surface, that hidden water could fill the world's oceans several times over. It is a sea without waves, stored not in caverns or pools, but in chemistry, a molecular ocean beneath our feet. The idea of deep water once seemed impossible. For centuries, scientists imagined the mantle as bone-dry its heat, and pressure too extreme for water to survive. But in 2014, a small blue crystal changed everything. It was a diamond from Brazil formed deep within the mantle and carried upward by volcanic eruption. Inside it lay tiny inclusions of ringwoodite containing measurable water, direct proof that Earth's interior is not arid but hydrated. In that gem, the hidden ocean glittered for the first time in human hands. How did it get there? The answer lies in the same process that drives the great cycles of creation and destruction: subduction. As oceanic plates dive into the mantle, they carry with them sediments, hydrated minerals and seawater trapped in pores and fractures. Under heat and pressure, those minerals release their water, which is then absorbed by mantle rocks. Over millions of years, this subducted water accumulates in the transition zone, creating a vast invisible reservoir. Some of it eventually rises again in plumes of magma, feeding volcanic eruptions and replenishing the surface oceans. Thus, the water cycle does not end with rain or sea. It continues downward into the planet's depths, a circulation of liquid vapor and crystal that binds the interior and the surface together. This hidden ocean helps explain one of Earth's greatest mysteries: why our planet has oceans at all. The other terrestrial worlds, Mercury, Venus, Mars, either lost their water or never held much to begin with. Without a deep storage system to recycle it, their surface water escaped into space or was locked permanently in minerals. Earth, by contrast, seems to have been designed for hydration. The same tectonic processes that reshape continents also maintain our seas. Water descends with subducting crust hides within the mantle's mineral cages, then returns through volcanoes and mid-ocean ridges. The oceans above exist because the one below never sleeps. The presence of water deep in the mantle also changes how the planet behaves. Even small amounts can lower the melting point of rock, making it easier for magma to form. Water softens the mantle's texture, allowing plates to move and subduction to continue. It lubricates the planet's interior, keeping tectonics alive. Without that hidden moisture, Earth might have cooled into rigidity long ago, a quiet, motionless sphere like Mars. In this way, the deep ocean is not only the source of surface water, but the enabler of the very system that renews it. And perhaps most astonishing of all, this buried ocean participates in life's story. The volcanic gases that built our atmosphere, the rains that carved rivers, even the water in our blood, all may have cycled through the mantle at some point. Every drop we drink might once have been part of a mineral deep within the planet, compressed, heated, and reborn. The ocean inside and the ocean outside are not separate, they are two halves of the same pulse. We tend to picture the Earth's interior as dry fire, but that is only half its truth. The mantle breathes water, its minerals absorb and release it like a living sponge, regulating the planet's surface climate over eons. When volcanoes erupt, they exhale that hidden ocean as steam. When rain falls, it begins the long journey back down, carried by rivers, sediments, and subducting plates to be folded again into the deep. If you could see through the crust, you would glimpse this secret hydrosphere, shimmering molecules imprisoned in crystal, diffused through vast plains of mineral grains, silent but essential. It is the ocean without color, without surface, without sound, the memory of water embedded in stone. The next time you stand by the sea and watch the waves roll in, remember what you see is only the surface of a much greater tide. Beneath every continent, every mountain and trench, the planet is soaked with its own ancient rain, hidden from sight, yet holding the key to why the world remains blue. Far beneath the dusty hills of northern Mexico, under the silver mines of Nacre, lies a world that seems carved not by geology, but by dreams. The air there is thick with heat and humidity, so fierce it fogs camera lenses in seconds. Yet through that mist, something shimmers, immense, luminous pillars that stretch like frozen lightning through the darkness. These are the giant gypsum crystals of the Cave of the Crystals, some over 30 feet long, each one glowing faintly like glass lit from within. Standing among them feels like stepping inside the lungs of the earth itself, a vast cathedral where time slowed to a crawl and minerals became architects of the impossible. The story of this underground cathedral begins not with beauty but with chemistry and patience. Hundreds of thousands of years ago, Naka was a furnace. Magma pulsed deep below the Chihuahua desert heating groundwater until it seethed with dissolved minerals. Among them was calcium sulfate, which under the right conditions forms the mineral gypsum, the same material used in plaster and alabaster. Normally gypsum crystallizes quickly into small opaque grains, but in Naka's hidden chamber something rare occurred. The temperature and the saturation of the mineral-laden water remained nearly constant, about 58 136 degrees, for hundreds of thousands of years. That delicate stability created a perfect equilibrium. Too hot and crystals would dissolve, too cold and they would form rapidly and imperfectly. But here, balanced on the edge between dissolution and growth, gypsum molecules found the time and stillness they needed. Over the millennia they assembled in exquisite order, stacking molecule upon molecule, elongating into clear flawless blades. Each beam of crystal is a monument to patience measured in geologic time, a record of chemistry allowed to breathe without disturbance. The chamber remained sealed in darkness, flooded by this mineral-rich broth, until human hands pierced it. In the year 2000, miners drilling a new tunnel for silver struck a hollow space and the temperature burst out like a furnace door opening. When they stepped inside, their headlamps revealed a sight beyond imagination. Colossal, transparent crystals crossing the chamber in every direction, intersecting like the ribs of a sleeping titan. Some were as thick as trees, others so clear that you could see your reflection inside them, distorted by time. The conditions inside the cave are nearly uninhabitable. The air is 90 to 100% humid, and the temperature hovers near the upper limit of human endurance. Within 10 minutes, unprotected visitors can collapse from heat exhaustion. Scientists who study the cave wear refrigerated suits and carry their own oxygen, moving slowly to avoid fogging their visors. Every minute spent among the crystals feels like walking through the breath of the planet itself, dense, ancient, and alive. Gypsum at its core is simple calcium, sulfur, oxygen, hydrogen elements, forged in stars and recycled through oceans and rocks. Yet under Nika's conditions, these humble ingredients became something transcendent. The crystal's transparency is so pure that when light strikes them, it seems to shimmer from within rather than reflect off their surface. Each one captures the story of water evaporating, condensing, and reforming over ages. Trapped bubbles contain ancient droplets, samples of liquid that have not touched the surface in 500,000 years. Within those bubbles, scientists have even found dormant microbial life organisms that may have survived in isolation longer than civilization itself. In the stillness of Naka, life and mineral intertwine, hinting at the blurred border between the organic and the inorganic. Some researchers call it a natural laboratory of extremophiles, life adapting to heat confinement and darkness. Others see it as a metaphor, proof that creation doesn't always require movement or light. Sometimes perfection grows in silence. Eventually, mining pumps that kept the tunnels dry were shut off, and the cave began to refill with warm and mineral-rich water. The crystals are safe now, sealed once again in their natural climate, continuing their imperceptible growth. In a sense, the cave has gone back to sleep, returning to the same still patient rhythm that shaped it for hundreds of millennia. If you could stand there now, deep below the desert, you would see nothing but pale water lit by your own reflection, and beneath it those giant beams resting in silence like the bones of light itself. The air would be thick, heavy with mineral scent, and the temperature would press against your skin like the breath of an ancient world. You might feel time expand around you, each second stretching thin till it feels like eternity. Naka's Cave of the Crystals is a reminder that even within the harshest conditions, beauty can bloom through patience and precision. It is the planet's slow heartbeat made visible, the artistry of equilibrium, the poetry of minerals aligning in perfect order over spans of time beyond comprehension. In the end, these immense pillars are not merely rock, they are time-given form, the silent song of a planet that never stops creating. If you could stretch your life across 1,000,000 years and watch the planet breathe in slow motion, you would see something extraordinary: rocks that flow like water, Mountains bending, valleys rippling, layers of salt rising through solid stone as if defying gravity. In the realm of geological time, nothing is as rigid as it seems. Under immense pressure and the patience of ages, even stone learns to move. One of the most remarkable expressions of this slow motion is the salt dome, a colossal structure born from the ancient marriage of ocean and desert. Millions of years ago, shallow seas evaporated under relentless sun, leaving behind vast beds of salt and other minerals. Over time, newer layers of sand, clay and rock buried these salt plains. But salt has a secret. Though solid, it is far less dense than the rocks above it, and under pressure, it behaves like a viscous fluid. It does not shatter, it flows. Slowly, inexorably, it begins to rise. Picture this buried salt as a thick, glowing syrup trapped under a heavy crust. As the weight builds, the salt squeezes upward through cracks, folding and warping the layers above. The process takes millions of years, but its result is breathtaking, a salt dome sometimes miles wide, pushing up through the strata like a bubble beneath wallpaper. From above, it may appear as a gentle hill, but beneath the surface, it's a towering column of migrating minerals still climbing toward the light. These domes have shaped landscapes, trapped resources, and rewritten the map of entire regions. Along the US Gulf Coast, hundreds of salt domes rise beneath Louisiana and Texas. Some pierce the surface as shimmering white mounds, others remain hidden, but influence everything above them. Oil and gas, lighter than rock but heavier than salt, often become trapped at the dome's edges, pooling in perfect geological vaults. Without these silent movements of salt, many of the world's great petroleum reserves might never have formed. What industry calls a reservoir is in truth a monument to the slow dance of minerals under pressure. To stand atop one of these domes is to feel nothing unusual. The ground seems still. But deep below, the earth moves with a patience beyond imagination. Instruments have measured salt domes rising at rates of a few millimeters per year, no faster than your fingernails grow yet. Over time, that motion can fracture overlying rock, create valleys or lift entire coastlines. In some regions, the upward flow even affects groundwater, bending it into strange patterns, or concentrating minerals into new deposits. The physics that allows this movement is both simple and sublime. All solids can deform under enough pressure and time, a property known as plasticity. Inside the Earth, where temperatures and pressures soar, rock ceases to behave like the brittle crust we know. Instead, it flows grains, sliding past grain molecules, migrating within crystals, atoms rearranging themselves like an invisible tide. The process is unimaginably slow, yet unstoppable. This is how mountains fold, how mantle convection stirs continents, and how salt domes rise like frozen fountains in the dark. In the laboratory, scientists have recreated this flow with cylinders of salt, placed under steady pressure. Over weeks, they watch the surface sag and creep, the salt reshaping itself like chilled honey. What unfolds in days under mechanical stress mirrors what happens in nature over millennia. It is a humbling sight, solid ground surrendering to time, revealing that even the strongest materials contain within them a quiet willingness to change. But salt is more than a mineral curiosity. It is a memory of vanished seas, the residue of oceans that once breathed and evaporated beneath ancient suns. Every dome that rises is a monument to a world long gone, each grain of halite a crystallized droplet of water from a sea that no longer exists. When the domes pierce the surface, they bring that ancient water back to light, gleaming white against desert and marsh. In the Persian Gulf, in Texas, in Iran, such formations shimmer like ghosts of primordial shores. Salt domes have also become laboratories for humanity's own relationship with deep time. Because salt is nearly impermeable and self-sealing engineers have used its depths to store oil gas and even radioactive waste. The same slow flow that bends rock can also heal cracks, making these caverns secure vaults for centuries. The Earth, which has long held the memory of its own oceans, now holds our industrial ambitions as well. In a way, our species has learned to borrow the planet's patience to use the movement of stone to guard what must not escape. There's poetry in this paradox. Salt, the substance we scatter on food and snow, is also a creature of eternity, a solid that flows, a crystal that moves. It teaches a lesson that repeats across geology. Time changes everything, not by violence, but by persistence. Under enough pressure and enough years, even mountains melt without melting. Imagine placing your hand on a rock and knowing that imperceptibly it is shifting beneath your touch, not because of erosion or earthquake, but because gravity and temperature are whispering through its structure, asking it to yield. To see stone not as dead, but as slow alive in its own rhythm, is to glimpse the true nature of the planet. The next time you hold a grain of salt between your fingers, think of it not as something fragile or fleeting, but as a drop of an ancient sea part of a mineral current that still moves through the earth. Somewhere below, vast columns of the same material are rising in darkness, bending rock like clay, reshaping the ground in utter silence. The world you walk on is not fixed. It is flowing slowly, endlessly, beautifully. Every forest you walk through today will one day vanish, but not in the way you think. Trees do not merely fall and rot. Some are chosen for another kind of afterlife, one where time and mineral join forces to turn the living into the eternal. This is the slow alchemy of petrification, the transformation of wood to stone, of life to quartz. It is Earth's way of keeping memory long after flesh, leaf and bark have dissolved. In the beginning, there is only a fallen tree buried quickly beneath ash or sediment. Perhaps it is caught by a volcanic eruption, like those that smothered the forests of ancient Arizona, or drowned in a floodplain and sealed from air. The key is exclusion. Oxygen must be cut off so that decay halts. Then the real work begins. Water rich in dissolved silica and minerals seeps through the buried wood. Over centuries it infiltrates every cell, every vein and pore. Bit by bit the organic matter is replaced by silica, sometimes mixed with iron, manganese or copper, that lend the stone its colour. Molecule by molecule, the tree becomes agate, jasper or opal. Its growth, rings preserved its bark texture, fossilized in crystal. The original structure remains so faithful that you can count the tree's age as if it were still alive, tracing its seasons of growth, frozen in mineral memory. Where once sap flowed quartz now glitters. Where once light passed through leaves, now it refracts through stone. The result is the petrified forest, a gallery of ancient sunlight caught and solidified by time. The same transformation unfolds on grander scales across geologic history. What begins as living matter trees, algae, plankton, peat, sinks into the Earth's layers and undergoes compression, heat and chemistry until it becomes rock. Coal is not merely blackened wood. It is the condensed essence of carboniferous swamps, their lush forests buried and pressed into gleaming seams. Each piece of coal is the residue of vanished jungles where dragonflies with 2-foot wings once drifted over fern trees. The carbon atoms within it once belonged to chlorophyll and leaves, to cells that drank sunlight and exhaled oxygen. Under deeper burial and greater pressure, even the tiniest life, the shells of plankton and microscopic algae, becomes oil and gas. On the seafloor, their remains settle into an organic mud that over millions of years is cooked by Earth's internal heat. Hydrogen and carbon reassemble into liquid chains, hydrocarbons that migrate upward through rock pores until they collect in traps and domes. Every drop of crude oil, every flicker of natural gas flame is ancient sunlight released again, energy first captured by photosynthesis hundreds of millions of years ago. In that sense, the fuels that power our cities are not products of industry but of biology. We are literally burning the past, the forests, the plankton, the long summers of the Paleozoic and Mesozoic worlds. The light from your desk lamp tonight began its journey in a Devonian swamp or a Cretaceous sea, travelling across epochs before it became flame or current. Humanity's modern age is a brief, brilliant flicker powered by ancient photosynthesis. Yet this transformation from wood to quartz life to stone also speaks to permanence beyond energy. Fossilized trees and coal seams are both forms of carbon, capture the Earth's own attempt to store away what life once drew from air. Over eons, tectonics and erosion may release it again, balancing the carbon cycle on scales we can barely imagine. Life breathes in carbon, geology breathes it out, and between them the planet keeps time. Petrified wood in its luminous stillness is the tenderest of paradoxes. It is both fragile and immortal. Touch it, and you feel something that was once alive. Look closely and you see cells preserved with atomic precision, as if the tree still waited for rain. Some pieces even preserve microscopic detail, xylem tubes, bark fissures, fungal traces, all transformed into quartz, yet unmistakably organic. The Earth remembers every line. There are petrified forests on every continent, the rainbow-hued trunks of Arizona's painted desert, the ghostly white logs of Argentina's Patagonia, the submerged woods of Egypt's deserts where ancient rivers once flowed. Each one tells the same story, life buried, not lost, translated into mineral language. Coal oil, petrified wood, and even limestone reefs share a single origin, the will of the planet to preserve. What was once soft becomes hard. What was fleeting becomes fixed. The very stones we build our cities from were once living creatures, compressed coral skeletons and algal shells fused into limestone. Every cathedral wall, every marble statue is made from the bodies of ancient seas. To hold a piece of petrified wood in your hand is to hold two kinds of time at once. One is biological, the rings of seasons, the story of rain and drought written in wood grain. The other is geological, the story of burial heat and crystallization that followed. Together they form a bridge between worlds, living and mineral, organic and eternal. The earth, it seems, never wastes its creations. It transforms them. Forest becomes stone, plankton becomes light, sunlight becomes motion. In every piece of coal, every polished slice of agate, there is a continuity matter, reimagining itself in slower rhythms than ours. Perhaps when seen in this light, nothing truly dies. It only changes form, waiting for another dawn. The tree that once reached towards sunlight now rests as quartz in the desert, gleaming under the same sky it once touched. Life becomes stone, stone becomes history, and the planet, endlessly patient, keeps every story it has ever told. If stone is the planet's memory, then sand is its whisper. It is the language through which mountains speak to the sea, a poem written in grains, each one the fragment of a journey that began in fire and will end in foam. To the untrained eye, sand seems simple dust beneath our feet, filler between toes. But each particle carries a biography written in mineral and time. The desert is not emptiness. It is a library of pulverized worlds. Every grain of sand begins as something far greater. A granite cliff, a volcanic field, a coral reef. Wind, water and frost attack them relentlessly, breaking their crystalline order into fragments. Quartz, the most durable mineral on Earth's surface, often endures longest resisting dissolution, while softer companions crumble. Over millennia, rivers grind rock into pebbles, pebbles into silt, silt into glittering dust. In that slow dance of attrition, mountain becomes memory, and the planet learns the art of reduction. Stand in a desert and you stand among the ruins of continents. Each dune is a museum of what once towered high above its particles, older than the desert itself. Under the microscope, these grains reveal their individuality, some clear as glass, others frosted, some sharp-edged, and new others rounded and polished by endless collisions. The more rounded the grain, the longer its voyage. The Sahara, the Gobi, the Arabian sands. Each is a congregation of survivors, a collection of minerals that refuse to vanish. But sand is not merely the residue of destruction, it is also a medium of transformation. When the wind moves across dunes, it behaves like a living thing. The surface ripples with patterns as regular as heartbeat and breath. Grains hop and roll, bouncing in arcs that trace invisible music across the landscape. In some deserts, that motion creates an audible phenomenon, singing dunes. When dry grains slide down a steep slope, their friction produces a low resonant hum, a deep note that can last for minutes. To stand among such dunes is to feel the earth singing through its smallest particles, a chorus of friction and resonance born from sunlight and wind. Beaches too are poems written in colour. The white sands of tropical islands shimmer with pulverized coral, and shells, the skeletal remains of marine life bleached by salt and sun. Black sands like those of Hawaii and Iceland tell of volcanic origins born from basalt shattered by surf. Red and pink sands carry iron from ancient rock, while green beaches such as Papacolia in Hawaii glimmer with olivine crystals that once cooled inside a volcano's heart. Each hue is a stanza in Earth's long composition, written where land and sea embrace. If deserts are the galleries of erosion, beaches are the stage where its performance concludes. Waves sort particles with mathematical grace, coarse grains settling first, fine ones carried farther by each retreating tide. The ocean's edge is a perpetual metronome measuring the rhythm of dissolution. What the mountain lost to rain, the shore redeems in shimmer. Yet even sand, the epitome of smallness, can still shape the world. Desert winds sculpt dunes hundreds of meters high, their crests migrating across continents. The sand from the Sahara travels in clouds across the Atlantic, fertilizing the Amazon rainforest with iron and phosphorus. In every breath of wind that carries dust, continents feed one another, completing a cycle as intimate as respiration. The planet exhales sand, another region inhales fertility. In human hands, sand takes on a second life. Melt it and it becomes glass, a transparent solid that bends light and thought alike. Our windows, microscopes and telescopes are all crystallized sand, allowing us to see both the smallest cells and the farthest galaxies. The very substance that erosion reduces from mountain to grain becomes the medium through which we expand our vision of the universe. In that transformation lies a quiet metaphor, fragility turned into clarity, impermanence made permanent. To hold a pinch of sand is to hold the planet's autobiography condensed to dust. Some grains may have fallen from Himalayan granite, others from volcanic ash or coral reefs long vanished. They have tumbled through rivers, deserts, glaciers and seas, surviving heat, cold and pressure. They are time-made, tangible history you can pour through your fingers, and when the wind finally lays them down, their rest is only temporary. Tomorrow another gust may lift them, another wave may scatter them anew. Sand is eternal, because it never settles. It only wanders. Listen closely on a quiet beach, and you can hear the faint hiss where waves withdraw the sound of billions of grains rearranging themselves. It is the smallest sound the earth makes, yet perhaps its most constant, the whisper of transformation. From mountain to sand, from sand to glass, from glass to vision, this is the poetry of erosion, the song of endurance written grain by grain. The dunes may shift, the cliffs may crumble, but nothing is lost. It only changes rhythm, form and name. Someday the sand beneath your feet will again become stone, and that stone may rise as a mountain once more. In that endless cycle of breaking and becoming, the earth reminds us that even its softest voices tell eternal stories, whispered, glittering, unending. Ice seems the very opposite of motion, still white, silent. Yet over time nothing moves like it. Nothing sculpts more patiently or leaves a deeper mark upon the world. A glacier is not a frozen sea, but a river of rock, a slow avalanche of memory that reshapes mountains and carries whole landscapes upon its back. It flows so slowly that to human eyes it appears still, yet its power rivals volcanoes and tides. In the arithmetic of deep time, ice is one of Earth's greatest artists. Every glacier begins with a snowfall that refuses to die. In the high valleys of the Himalayas, the Alps, the Andes and Antarctica snow piles faster than it melts. Layer upon layer, it compresses under its own weight. Air is squeezed out. Crystals fuse. The snow becomes firn and then glacial ice a dense blue, almost liquid solid. When the thickness surpasses a few dozen meters, gravity takes over. The glacier begins to move, pulled downhill by its own immense mass-bending rock and carving valleys as it goes. Though it seems solid, glacial ice behaves like a viscous fluid. Under pressure, its crystals deform and slide, allowing the glacier to creep forward at speeds measured in centimeters per day or in rare surges meters per hour. Beneath it, meltwater acts as a lubricant, letting the ice glide across bedrock with quiet grace. Over centuries, the glacier's path becomes a polished sculpture of stone, U-shaped valleys, sharp-edged ridges, hanging cirques. The Alps, the fjords of Norway, the Great Lakes of North America, all are signatures of this slow, cold art. To touch a glacial valley is to feel the passage of time itself. The rounded boulders, the striated cliffs, the smooth basin floors, each mark is a line in the glacier's calligraphy. Rocks caught in the ice's base act like chisels, grinding and scratching as they move. Over thousands of years, whole mountains are worn down, their dust carried away in rivers of meltwater. The ground beneath our feet in many lands is the dust of vanished peaks. But glaciers do more than carve. They remember. Locked within their frozen depths are bubbles of air older than civilization, tiny time capsules of vanished atmospheres. In Greenland and Antarctica, cores drilled from the ice reveal layers like pages in a book, each one a year's snowfall compressed into a translucent sheet. Within those layers lie traces of pollen ash and trapped gases that tell the story of our planet's climate, the rise and fall of carbon dioxide, the advance and retreat of cold ages. By reading them, scientists have learned to hear the rhythm of Earth's breath across hundreds of millennia. A glacier is thus both sculptor and historian. It reshapes the land while preserving its own past, erasing and recording at once. Its memory is vast, but also fragile. When climate shifts, glaciers retreat, releasing meltwater that feeds rivers and raises seas. The traces they leave behind, moraine ridges, kettle, lakes' erratic boulders, are the punctuation marks of an epoch's end. Each retreat reveals the bones of a world the ice once held. During the last ice age, 2 kilometers of ice covered what is now New York and London. Mountains that we consider timeless were smoothed and sharpened under its pressure. The continents themselves groaned beneath the weight, their crusts flexing downward like springboards. When the ice melted, the land began to rebound an elastic rise that continues today, centuries after the glaciers withdrew. The Earth, like its ice, moves slowly but never stops. Not all glaciers fade quietly. Some surge their pace, accelerating for months or years as meltwater builds beneath them, or as internal stresses realign their crystalline flow. When they surge, they advance like slow-motion avalanches, swallowing forests, grinding rock and pushing moraines miles forward. Then, as suddenly as they began, they halt, exhausted, frozen once more. These cycles of motion and stillness are the glaciers breathing a pattern older than language. The artistry of ice extends far beyond Earth. On Mars, in the shadows of Olympus, Mon's frozen glaciers lie buried beneath dust. On Jupiter's moon, Europa, an entire ocean of ice shifts and fractures in silence, sculpting alien ridges under a sun too distant to melt them. The same principles apply: gravity, pressure, time, the triad of movement that turns solid into fluid. Wherever there is ice and patience, there is sculpture. And yet, for all its slowness, glacial motion is alive. Satellite imagery shows the great Antarctic and Greenland ice sheets flowing outward like syrup, their surfaces crisscrossed by blue meltwater streams and crevasses that open and close with the seasons. From above, they resemble living tissues flexing, healing, reshaping. The Earth wears these frozen rivers like silver veins, carrying not blood but memory. To stand before a glacier is to witness time condensed into form. You can hear it creak and sigh like a house settling after a long day. The air around it feels ancient cold, not only in temperature but in meaning. And if you listen long enough, you may sense that the glacier is not retreating in defeat, but returning to its cycle: water to ice to river to sea to sky. Nothing is lost. When we speak of erosion, we think of destruction, but in truth, glaciers are creators. They dig valleys where forests will grow, scatter mineral-rich sediments that feed soil, carve basins where lakes will shine. The shapes they leave behind, fjords, drumlins, cirques, are the fingerprints of cold upon creation. In their silence lies a paradox that something so slow, so cold can shape the face of the world. Ice remembers, but it also renews. It writes its story on stone, and sky then melts back into the rivers that will one day feed new forests, new life. To walk through a glacial valley is to walk inside a memory millions of years long, one carved not by violence, but by persistence. And so the planet turns, carrying in its frozen heart the memory of all it has shaped. When the ice melts, the water flows on. The artist never truly leaves, it simply changes tools. Not all of Earth's memories are carved in mountains or sealed in ice. Some are as fleeting as a footprint, as light as a falling drop. Yet against all odds, even the most delicate moments sometimes endure. A raindrop splash, a bird's feather pressed into mud, the shadow of a leaf. These are the planet's whispers of transience, fossils so fragile they seem impossible. They are not monuments of time, but its breath caught mid-air. Imagine a storm 100 million years ago. Rain falls on a muddy floodplain, pocking the surface with tiny craters. Then before wind or sun can erase them, a thin layer of silt drifts over, sealing them like pressed flowers between pages. As eons pass, the mud hardens into stone. When paleontologists split that stone open today, they find what looks like constellations of tiny circles, fossil raindrops, the echoes of a vanished sky. Each ring records the instant when water met Earth, a translation of weather into geometry. From the size and depth of the impressions, scientists can infer the height of clouds, even the density of ancient atmospheres. In one outcrop in India, raindrop fossils nearly 2 billion years old whisper of a young planet just learning to rain. They are the oldest known record of weather, a chapter of air turned to stone. Other traces preserve something even more miraculous, the memory of life's softness. When a feather or a leaf or a jellyfish touches the sediment just before burial, it can leave a film so thin that only its chemistry survives. In some cases, minerals replicate it molecule by molecule, iron and manganese, taking the place of tissue carbon films, forming silhouettes so fine that even the barbs of a feather can be seen. The most famous of these marvels are the fossils of Archaeopteryx discovered in the fine limestone of Solnhofen, Germany. These slabs, once part of a Jurassic lagoon, hold impressions so detailed that you can trace each quill of the wings, every contour of the body. When light glances across them, the shadows of feathers seem to shimmer as if ready to lift once more. The rock captures not just anatomy but motion, the gesture of flight arrested mid-beat. In the same beds, paleontologists have found dragonflies with gauzy wings intact, the delicate lines of fish scales, even the ripples of water frozen in time. These formations owe their preservation to extraordinary calm, stagnant lagoons where oxygen was scarce, decay was slow, and sediments were as fine as dust. Every layer was a page turning only once every few centuries. When creatures fell into that quiet mud, they were embalmed by stillness itself. Soft tissue fossils are the planet's rarest miracles. Flesh usually vanishes within days, consumed by bacteria and time. Yet under the right chemical spell, anoxic water, rapid burial, mineral-rich mud life can linger. In the Burgess Shale of Canada, 500 million years old, entire ecosystems of jelly-bodied creatures were preserved in exquisite detail, their guts, gills, and eyes outlined in carbon films. Each fossil there is a paradox, the frailest forms outlasting stone. Even in more recent strata, whispers of skin and muscle survive. In Mongolia's Gobi Desert, paleontologists have uncovered dinosaur mummies so complete that the texture of their scales remains visible, their claws still curled in mid-stride. In some pigments endure molecular ghosts, revealing the colours of feathers, the pattern of stripes or spots that vanished before humans ever existed. These discoveries have rewritten how we imagine prehistoric life, restoring its colour, its texture, its warmth. There are fossils that preserve not only the form but the behaviour of vanished beings. The imprints of a herd of dinosaurs wading across a riverbank, the paired trails of trilobites moving side by side, the looping path of a worm through ancient mud. Each is a gesture of motion, fossilised as if time itself paused to take a breath. Even the scratches of claws or the drag of a tail across the ground become messages sent across eons, proof that something alive once felt the weight of gravity in that exact place. But perhaps the most poetic of all are the moments of intimacy caught forever. Two ancient fish locked in the instant of mating, a predator and prey entombed together in the act of struggle, the outlines of leaves pressed against one another as if holding hands. Such fossils remind us that the boundary between life and rock is thinner than we think. The Earth does not forget quickly, it remembers in layers in chemistry and patience. To find such a fossil is to hold a paradox in your hands. What should have been ephemeral, a raindrop, a feather, a heartbeat, has become immortal. Each one is a signature of fragility preserved by the planet's gentlest alchemy. The same forces that erase mountains can under rare circumstances protect the lightest touch. And when you look at these traces under light, something uncanny happens. The shadow of a feather or the ring of a raindrop seems to glow faintly as though time itself was shining through. It is not just stone you are seeing, but memory turned visible, the Earth remembering the softest parts of its own story. Every fossil raindrop, every feather shadow, every faint film of carbon reminds us of the same truth, that even the most delicate things leave a mark. Life in all its vulnerability imprints itself upon eternity. The next time rain falls and darkens the ground for a moment before drying away, think of the chance 1 in a billion that somewhere a drop like that once struck ancient mud and never disappeared. The world keeps records in ways we barely comprehend. Some are mountains, some are glaciers, some are no more than the weight of a single raindrop on fresh earth remembered forever by stone. There was a time when the earth itself almost died. Long before forests and fish, before shells or bones, before even the simplest animals swam through ancient seas, the planet slipped into a silence so deep it nearly erased all movement. The oceans froze to their floors, glaciers crept across the equator, and sunlight scattered uselessly from a world of ice. For tens of millions of years, the Earth lay trapped in white. Scientists call this epoch Snowball Earth, and it is both a warning and a miracle, the story of a planet that froze and then awoke to invent complexity. It began more than 700 million years ago during the late Proterozoic Eon, when the continents were gathered near the equator. The sun was weaker, then shining only about 94% as bright as it does today. If the balance of atmosphere, ocean and cloud faltered even slightly, the planet could cool rapidly, and so it did. Volcanic eruptions and the weathering of rising mountains drew carbon dioxide from the air, thinning the greenhouse blanket that trapped warmth. Ice began to spread from the poles. As it expanded, its bright surface reflected more sunlight back into space, accelerating the chill. Within a geological heartbeat, the feedback loop spiraled out of control. Soon the entire planet was rimmed with glaciers. Equatorial seas froze solid. Temperatures plummeted to 50 degrees. Beneath the ice, the oceans turned dark and still. Photosynthesis dwindled, oxygen levels fell. From space Earth would have gleamed like a marble of pale blue glass, beautiful, lifeless, silent. The continents were buried beneath kilometers of ice, their mountains reduced to white dunes. Even the equatorial waters, once warm and green, lay under sheets thick enough to bear mountains of their own. And yet life did not die. Beneath cracks in the ice, where sunlight still filtered weakly through thin patches, microscopic algae clung on. Around volcanic vents on the ocean floor, bacteria thrived on chemical energy defying the cold. These survivors were the seeds of everything to come. The Earth was frozen on the surface, but within its heart still burned. Deep inside, the mantle continued to convect and volcanoes continued to erupt. Though their ash was quickly trapped under ice, their gases, especially carbon dioxide, had nowhere to go but up. Normally CO2 would dissolve into rainwater or oceans and be recycled by life. But under a frozen world, those processes stopped. The gas accumulated for millions of years, thickening the atmosphere like an unseen breath. Slowly the greenhouse returned. Then one day, if day can describe a turning point millions of years long, the ice began to lose. The planet reached a critical threshold where sunlight and greenhouse warmth combined to melt the glaciers from below. The frozen oceans cracked open. Liquid water, dark and heat-absorbing, spread across the surface again. The feedback reversed. The more it melted, the warmer the planet grew. In geological moments, the Earth thawed. The aftermath must have been cataclysmic. Torrents of meltwater carved canyons across continents. The ocean, newly free, boiled with carbon dioxide and minerals released from the ice. As the planet warmed past balance, temperatures may have soared to tropical extremes. Acid rains fell, dissolving rock and flooding the seas with calcium and phosphorus. And in that turbulent chemistry, life found its second wind. Geologists find the evidence of this transformation written in stone. Beneath ancient dolomite cliffs, they see thick deposits of cap carbonates, sheets of limestone, that could only have formed when the ocean suddenly filled with dissolved carbon and calcium after a deep freeze. Above those layers appear fossils of multicellular algae and early animals. From the wreckage of ice, life diversified, reorganized, and began to experiment with complexity. The thaw of Snowball Earth may have been the prelude to the Cambrian explosion, that sudden flowering of form and function that filled the oceans with eyes, limbs, shells, and nerves. It is strange to think that a near-death experience could be the catalyst for creation, yet it fits the planet's rhythm: destruction and renewal, freeze and thaw, silence and song. The cold may have purified the oceans, oxygenated them, and prepared them for new metabolism. It may also have created environmental stress that favored innovation, forcing single-celled organisms to cooperate, to share resources, to form colonies that eventually became the first animals. Even now, the scars of Snowball Earth remain. Ancient rocks in Namibia, Canada, and China bear glacial striations where ice once scraped the seafloor at tropical latitudes. Dropstones boulders carried by icebergs and dropped into marine sediments appear where no glacier should have reached. They are the fingerprints of a world that froze solid and somehow survived. The story of Snowball Earth carries an eerie poetry. It tells us that the planet is not fragile but dynamic, capable of swinging between extremes, yet always finding equilibrium again. It tells us that life is tougher than imagination, that it can hibernate through catastrophe and reawaken stronger. And it tells us that catastrophe itself can be fertile, that even global stillness can be the womb of motion and death, the architect of evolution. If you could have stood on the surface during those last moments of thaw, you would have seen a sky of orange haze and rivers of steam racing through valleys newly exposed. The ice would have groaned and collapsed, carving into waves that thundered against granite. And beneath that chaos, tiny organisms would have stirred in the meltwater, drinking sunlight for the first time in millions of years. From their fragile renewal came everything: forests, coral reefs, cities, ourselves. The planet that froze did not perish. It dreamed. And when it awoke, it painted the world anew. Before the skies were blue, before rust existed, before lungs or leaves, or even the concept of air, the Earth exhaled something else. Methane and carbon dioxide filled the atmosphere, and the oceans were as dark and heavy as syrup. Iron-rich alien, tinted a deep poisonous green. Lightning flickered through a haze of volcanic gases. The young planet was alive, but not yet breathing in any way we would recognize. Then slowly, silently, life itself began to teach the Earth how to breathe. The teachers were microscopic cyanobacteria, tiny architects of the impossible. Floating in shallow seas 3.5 billion years ago, They learned a trick that would transform everything they discovered: how to capture sunlight and split water. This process, photosynthesis, was the first true alchemy of life, taking light, water, and carbon dioxide and turning them into sugar and oxygen. At first, that oxygen seemed to vanish as soon as it appeared. The early oceans were full of dissolved iron, and every atom of oxygen that escaped the bacteria's cells immediately bound with it, forming iron oxide's rust. The results of that ancient chemical war still gleam today in the banded iron formations that stripe the world's oldest rocks, alternating layers of silver-grey hematite and red jasper laid down like pages in a book. Each band marks a breath, the pulse of photosynthetic life meeting the ocean's metal heart. For billions of years, these formations accumulated, the Earth quietly recording the story of its transformation in red and grey stone. At first, the planet barely noticed. The oxygen produced in the seas was consumed as fast as it was made. But cyanobacteria multiplied, coating tidal flats in mats and forming the first stromatolites, layered reef-like structures that still grow today in a few shallow bays of Australia and the Bahamas. Slowly, their work outpaced the planet's appetite for reaction. When the iron was finally used up, oxygen began to escape first into the water, then into the air. What followed was both triumph and tragedy. Around 2.4 billion years ago, the world experienced what scientists call the Great Oxidation Event. Oxygen levels in the atmosphere surged for the first time. The skies shifted from hazy orange to pale blue as methane was destroyed and replaced by carbon dioxide and nitrogen. For organisms that had thrived in an oxygen-free world, this was a catastrophe. Oxygen for them was poison, corrosive, reactive, lethal. Entire microbial kingdoms vanished, smothered by the byproduct of another species' metabolism. It was in effect the planet's first mass extinction, and yet it was also the beginning of the modern world. The new oxygen reacted with ultraviolet light in the upper atmosphere, creating the ozone layer, a shield that would one day allow life to venture onto land. The ocean's chemistry changed. Minerals that had been soluble in anoxic water began to precipitate and settle. The seas turned from green to blue. For the first time, iron rusted in open air. The planet's surface learned colour. Oxygen transformed not just the environment, but the possibilities of energy itself. Metabolism that once relied on inefficient fermentation suddenly gained a 100-fold advantage. Cells that could tolerate oxygen harnessed its power to burn food, internally producing more energy per molecule than ever before. This metabolic leap paved the way for complexity, for larger cells, nuclei, multicellular cooperation. The breath of oxygen was the spark that made animal life and ultimately consciousness possible. The transition was not sudden. It took hundreds of millions of years for oxygen to stabilize in the atmosphere. At first, it fluctuated wildly, rising and falling like a planet learning to inhale and exhale. Volcanoes belched, reducing gases that tried to pull the oxygen back down. Oceans absorbed it greedily, storing it in minerals. But the cyanobacteria never stopped their quiet labor. With every dawn, they split more water, released more breath, and turned the world a little more transparent. Even today, their descendants continue that ancient work. Every second, billions of cyanobacteria in the oceans exhale the air we breathe. Half of the oxygen in your lungs at this moment came not from forests, but from microscopic marine plankton performing the same chemistry perfected billions of years ago. Every breath we take is a conversation with their ancient lineage, a continuation of that first planetary exhalation. It is humbling to realize that the color of the sky, the shimmer of rust, and the fire in our cells all trace back to that microbial revolution. The Great Oxidation Event was not a sudden miracle, but a patient act of persistence, a quiet rebellion by life against its own limitations. The Earth's first blue sky was painted not by weather but by bacteria. If you could stand on a shore, then you would see a world both alien and familiar. The sea, once murky green, would gleam faintly under a sun newly brightened by clearer air. The rocks would blush with red oxide. The smell would be metallic sharp, the scent of oxygen meeting iron for the first time, and in the shallows films of microbial mats would flutter gently, catching light and releasing the breath that would one day fill lungs and kindle fires. The Earth did not gain an atmosphere. It grew one nursed by the smallest creatures imaginable. It was an act of photosynthetic faith that reshaped chemistry, geology, and destiny. The planet learned to breathe, and in doing so prepared the way for all who would breathe after it. The Earth has never been still, not for a single moment, in 4.5 billion years. Beneath our feet, continents drift like rafts on a restless sea of mantle. Mountains rise and crumble, oceans open and close, and the map of the planet redraws itself again and again. What we call continents are not fixed homelands, but travelers caught in an endless dance, colliding, parting, and reuniting in cycles so vast that entire lineages of life rise and vanish between steps. To see this dance clearly, you must abandon human time. Imagine millions of years compressed into seconds. The continents glide like living creatures, curling and folding, merging into single land masses only to split apart again. These grand assemblies are called supercontinents, and their story is the slow heartbeat of geology, the rhythm by which Earth renews itself. The cycle began deep in the planet's youth nearly 2 billion years ago with a continent we call Nuna, or Columbia. It formed when smaller cratons' ancient continental cores collided in a ring of fire, forging mountain belts that once towered higher than the Himalayas. Nuna's existence is known only from magnetic signatures and scattered rocks, now found on every continent. For hundreds of millions of years it sprawled across the equator, a single landmass surrounded by an endless global ocean. Then, as heat built beneath its crust, it cracked apart. Rifts opened, and Nuna drifted away into memory. After it came Rodinia, around 900 million years ago, a vast continent whose name means to be born together. It gathered almost all the world's land into one enormous frozen expanse. Its breakup may have triggered the snowball Earth episodes as continents at low latitudes weathered quickly, pulling carbon dioxide from the air and cooling the planet. When Rodinia fractured, it did so dramatically. New oceans opened, fresh coastlines teemed with life, and the seeds of diversity were sown in the chemical churn of erosion and sunlight. Later, around 600 million years ago, a new configuration emerged. Pannosia short-lived and unstable, existing only tens of millions of years before collapsing into fragments. Those fragments eventually drifted into new collisions that gave birth to Pangaea, perhaps the most famous supercontinent, the one that left its imprint most vividly upon the present. Pangaea, formed about 335 million years ago, was a single world-spanning landmass shaped roughly like a colossal crescent. Its interior was dry and vast, a desert continent wrapped by one global ocean called Panthalassa. Across its breadth, mountain chains rose where continents had fused: the Urals in Eurasia, the Appalachians in North America, the Atlas Ranges of Africa. In its time, Pangaea held the great amphibians of the Carboniferous swamps, the early reptiles that would become dinosaurs, and forests that later became coal. It was both cradle and crucible, an Earth drawn tight into one enormous skin. But the planet's heat does not tolerate permanence. The mantle's convection cells, those colossal rivers of slow-moving rock, tugged and twisted the supercontinent from below. Around 175 million years ago, Pangaea cracked open, giving birth to the Atlantic Ocean, and setting the continents on their modern paths. Africa drifted north, South America west, Antarctica, and Australia south. The pattern of the world we know, its oceans, islands, and climates, was born from that shattering. This cycle of unification and dispersal repeats roughly every 400–600 million years. It is a planetary respiration driven by the deep currents of the mantle. Each supercontinent's breakup scatters landmasses that eventually reunite in new configurations. Already we can trace the next gathering. Over the next 200 million years, the slow drift of tectonic plates will carry Asia and the Americas together, closing the Pacific and forming a new supercontinent that scientists call Amasia. In that far future, the Pacific Ocean, shrinking by centimeters each year, will vanish, its seafloor subducted beneath encroaching coasts. The Atlantic may widen to its maximum and then begin to close. Greenland could fuse with Siberia, Alaska might weld to Japan. The world's geography will be reborn in a new pattern, the continents joined once again beneath a single sky. And when they do, the mountains of our age, the Andes, the Rockies, the Himalayas, will have long since eroded to plains, their minerals recycled into new peaks rising from the collision zones of tomorrow. These vast cycles, called the Wilson cycles, link the deepest interior of the planet to the surface we inhabit. They shape the atmosphere, and the climate supercontinents at high latitudes can plunge the world into ice ages, while their breakup floods the air with carbon dioxide from volcanic rifts, warming the planet anew. They guide the migration of species, the formation of resources, even the oxygenation of the air. Every epoch of life has unfolded upon a different map, each drawn by the same invisible hand of heat and time. To imagine Earth's continents from afar is to watch continents drifting like slow rafts on a molten sea, colliding with the solemn grace of continents meeting after lifetimes apart. It is the world as a dance, solemn, majestic, and eternal. Each impact builds mountains, each separation births oceans. Nothing is fixed, yet everything is cyclical. Even now, as we plant cities and borders and call them permanent, the continents beneath are already moving toward their next embrace. Africa is inching northward into Europe, lifting new mountains that will someday rival the Alps. Australia is drifting toward Asia, dragging coral reefs and deserts with it. The Atlantic continues to widen grain by grain as magma rises at the mid-ocean ridge. Our maps are momentary sketches on the skin of a restless world. The supercontinents of the past, Nuna, Rodinia, Pannotia, Pangaea, are not lost. They are simply parts of a longer rhythm. The continents we know are their fragments still dancing to the same deep beat. And when the next supercontinent forms, when a measure rises and the planet once again gathers itself into one Earth, will continue its endless choreography of renewal. To the planet, these collisions are not catastrophes, but acts of creation. Each union births mountains and ecosystems. Each breakup releases new seas and climates. The Earth's beauty lies in this motion, its refusal to stand still. From a cosmic distance, our world is not a static sphere, but a dancer swaying slowly in the dark, its continents gliding, embracing and parting in an endless, graceful rhythm. It is the music of heat, gravity and time, the endless continental dance that never stops. Every pebble, every mountain, every grain of sand beneath your feet is older than the Earth itself. The stones we hold are not merely terrestrial, they are cosmic heirlooms, fragments of a much older story written in starlight and fire. Long before the first ocean shimmered or the first continent rose, the elements that would one day become rock were forged in the hearts of stars. When you touch stone, you are touching the ashes of the cosmos. In the beginning, there were only hydrogen and helium, the simplest gases born from the Big Bang. Everything else, iron, silicon, carbon, oxygen, was created later, inside stars that lived, burned and died long before our sun was born. In their final moments, those stars exploded as supernovae, scattering their enriched cores across the galaxy. Shockwaves rippled through the interstellar medium, seeding it with the dust of future worlds, the iron that would become Earth's core, the calcium of our bones, the gold of our jewelry. Over billions of years, this stardust drifted, cooled and mingled. Then about 4.6 billion years ago, a small region of a spiral arm of the Milky Way collapsed under its own gravity. The collapse ignited a new star, our Sun, and around it a swirling protoplanetary disk of gas and dust began to spin. Within that disk, particles collided and clumped together, growing from grains to pebbles to planetesimals, tiny worlds of rock and ice. The collisions were violent and ceaseless. Heat melted the interiors of these young bodies, separating metal from stone, forming cores, mantles and crusts in miniature. Out of that chaos, the solar system took shape, the inner planets of rock, the outer giants of gas, and countless asteroids orbiting like debris of unfinished creation. Among those planetesimals, one grew larger, hotter, denser, our proto-Earth. But even that was not the final act. In its infancy, Earth collided with another Mars-sized body scientist called Theia. The impact was apocalyptic. Both worlds melted in an ocean of vaporized rock. From the debris, gravity gathered a new companion the Moon forged from the mingled flesh of both planets. The same stone that underlies your feet lies also beneath the lunar regolith. The Earth and the Moon are siblings born of the same wound. Their kinship is written in their identical isotopic fingerprints, proof that our planet's first act of creation was also an act of shared destruction. When the molten Earth cooled, heavy elements like iron and nickel sank to form the core, while lighter silicates floated upward to form the crust. Water and gases trapped inside early minerals escaped as steam and rain filling the atmosphere and oceans. But some of Earth's oldest survivors predate even this cooling. Tiny zircon crystals found in the ancient rocks of Western Australia are over 4.3 billion years old, older than any ocean, any mountain, any life. These microscopic gems, resistant to everything except time, contain within them traces of uranium that act as natural clocks. They tell us that by the time the Earth was only 200 million years old, liquid water already pooled on its surface. The planet, fresh from cosmic fire, was already learning calm. If you pick up a meteorite, you hold a sibling of the Earth, a piece of the same solar dust that never found a home in a planet. Some meteorites still carry chondrules, glassy beads of molten material that once floated freely in the solar nebula before fusing together. Others contain pre-solar grains, microscopic specks of carbon or silicon carbide, older than the sun itself, their isotopes whispering of supernovae and red giants far away. Each one is a time capsule, a physical message from before our world existed. The iron meteorites that occasionally fall to Earth are fragments of shattered planetesimals, ancient worlds, whose cores froze solid before being torn apart. Their metallic interiors, once hidden deep beneath surfaces like our own, now glitter under microscopes in crystalline patterns called Widmanstätten structures, the slow geometries of nickel-iron cooling over millions of years. They are the exposed hearts of lost planets. Even the very stones of the moon returned by Apollo astronauts echo this cosmic ancestry. Their chemistry matches Earth's mantle so precisely that scientists can trace both back to the same origin event. When you gaze at the full moon, you are not looking at something separate from Earth, but at a mirror reflecting our planet's earliest history, a second face of the same cosmic body. And scattered across our world, buried in sediments and mountain ranges, are the meteorites that kept arriving long after formation ceased. They seeded the young Earth with rare metals, carbon molecules, and perhaps even the first amino acids, the chemical preludes of life. In this way, stone became more than mineral, it became memory. Every atom of silicon, iron and oxygen in your body once floated freely between stars waiting for the right world to gather it. To think of stone as merely dead matter is to forget its origin. Every rock is a relic of stellar fusion, every crystal a frozen flame. The iron in your blood, the calcium in your bones, the phosphorus in your DNA, all were minted in stars that lived and died long before our sun was born. We are quite literally the descendants of stone and starlight. Even now, the process continues. Meteorites still fall through the night, their brief fire tracing a reminder of our cosmic inheritance. The dust that accumulates on rooftops every year includes particles older than Earth, drifting quietly down through the air we breathe. The solar system remains what it always was, a web of stone, iron and motion endlessly exchanging fragments of itself. If you could hold the oldest rock in your hand and listen not to its surface but to its atoms, you would hear echoes of collapsing stars, of nuclear forges humming in distant galaxies. You would hear the story of gravity gathering dust into worlds and worlds into the possibility of life. The Earth is not merely a planet, it is a piece of the universe remembering how to shine. Its mountains, its deserts, even the humble pebbles by the sea are fragments of eternity cooled enough to hold oceans and dreams. We walk upon the ashes of stars and they do not burn us, they hold us up. If the Earth could dream, its dreams would be made of stone. Every ridge and valley, every seam of quartz or ripple of shale would be a remembered thought, a trace of motion held in mineral language. Rocks are not dead things. They are the slow pulse of the planet made visible, the autobiography of a world that never stops writing itself. When you look at a mountain, you are seeing time, not height. You are seeing the rise and collapse of ancient seas, the breath of volcanoes, the weight of glaciers, the press of continents moving like continents of sleep. The granite in a single cliff may have crystallized while the sky was still unbreathable. The sand under your feet may once have been a mountain in Africa, a coral reef in the Pacific, a handful of dust in the tail of a comet. The landscape you inhabit is a library, each stone a page, each fault a margin note, each fossil a sentence written in patience. Geology is not merely the study of rocks, it is the study of remembrance. Every layer of the Earth's crust holds what the planet once felt. The banded iron of early seas remembers when oxygen was new. The limestones remember warm waters that no longer exist. The coal seams recall ancient forests whispering beneath tropical storms, and the black shales remember the stagnant darkness that followed. Even the smooth stones of a river remember motion, the way water once touched them, turned them, made them round. In this way, the Earth's memory is not like ours, it never forgets. It stores everything, not as stories, but as structure. When continents collide, they do not simply erase what came before, they fold it in. Mountains contain oceans. Oceans contain mountains ground to powder. The crust is a palimpsest written and rewritten, but nothing truly lost. The planet keeps every version of itself pressed into its own skin. And below it all, the mantle still breathes slowly, steadily, like the diaphragm of a sleeping creature. Convection currents rise and fall through molten stone dragging continents, creating oceans renewing the crust. What seems solid to us is in constant motion. The ground does not sleep. It merely moves too slowly for our eyes. Perhaps that is what makes geology so calming, its pace dwarfs all worry. To the mountains, our lifetimes are flashes of weather. To a basalt plain, a century is a passing breeze. Even the tragedies we call permanent erosion, extinction, collapse are only edits in a story that will continue long after we're gone. The Earth has endured bombardment, ice, fire, and still it endures. Its rhythm is patience embodied. Listen, and you can almost hear it, the faint hum beneath everything. The low tremor of tides in the crust, the deep whisper of magma cooling the long exhale of wind-carving stone. These are the sounds of a planet remembering itself. Every pebble on a beach, every crystal in a cave is a record of temperature, pressure, motion, and time. A pulse slowed to a geological heartbeat. In that sense, the ground beneath your feet is not separate from you. The calcium in your bones once belonged to coral reefs. The iron in your blood was forged in Earth's core or in stars before it. We are not guests upon this planet, we are its continuation. Our bodies are sediments of the cosmos, briefly animated, destined to return. When we breathe, we recycle ancient air. When we walk, we rearrange the dust of ancient mountains. We are the planet dreaming of itself. And when you lie still at night, listening to the faint ticking of your own pulse, you're closer to the Earth's rhythm than you realize. The same slow order governs you: growth, decay, renewal. Cells divide as crystals do. Heat rises and disperses. Even thought follows the gradient of energy, like water finding the lowest path. We are geologic beings made of living stone, temporary patterns of matter that the planet assembled for a little while to look around and wonder. So as this story closes, let the world quiet again. Picture the continents drifting under a blanket of cloud mountains, exhaling mist glaciers sighing into rivers. Beneath it all, the mantle glows softly unhurried, carrying on the work it began billions of years ago. This is the memory of rock, a memory that has no hurry, no fear, no end. It simply continues folding, cooling, breathing, eroding, creating. Every moment we call now is only the surface of a process that began before life and will persist long after. And yet in the stillness of that thought there is comfort. Because the same patience that shapes mountains shapes us too. Because nothing, not even stone, truly rests, it simply changes form. Because the Earth's memory holds everything, and we are part of that memory carried gently within its slow, luminous dream. Good night.